Come outside with me for a moment. Let's find a quiet place, far from the city lights, and just look up. What do you see? A velvet black canvas, punctured by 1,000 tiny jewels of light. There's a profound stillness in the night sky, a quiet that seems to stretch on forever. In that endless quiet, our minds, used to measuring the world in footsteps and heartbeats, start searching for patterns. We connect the dots, naming constellations after ancient heroes and mythical beasts. We find comfort in the familiar glow of the moon, our celestial companion on its nightly pilgrimage. Welcome to the Science for Deep Sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. But when we really try to comprehend what we're looking at, not just the points of light, but the spaces between them, our sense of scale begins to dissolve. We use words like vast, enormous, and infinite, but these are just placeholders, feeble attempts to label something that defies our lived experience. We think of mountains as immense, of oceans as boundless. But in the cosmic ocean, our entire planet, with all its mountains and all its seas, is less than a single, solitary drop of water. So, in a place where our planet is a speck of dust and stars are as numerous as grains of sand on all the world's beaches, what does largest even mean? What's the grandest thing we can point to in this incomprehensible expanse? This question has driven astronomers for centuries, pushing them to build ever more powerful eyes to peer deeper into the dark. And what they've found are structures so vast, so utterly monumental, that they seem to break the very rules of the universe itself. Tonight, we won't be in a hurry. We're going on a slow and deliberate journey, a gradual ascent from the familiar ground beneath our feet to the very edge of our understanding. Our destination is a silent, sprawling, and deeply controversial titan known as the Hercules Corona Borealis Great Wall. It's a journey that will challenge our perception of space, of time, and of our own place within this grand, silent, and beautiful cosmos. So, find a comfortable position, let your breathing slow, and allow your mind to expand as we begin our climb up the cosmic ladder. A foundation of scale, our home address. Our journey begins right here. Feel the solid ground beneath you, the gentle pull of gravity holding you close. This is Earth, our home, a sphere of rock and water, teeming with life, hurtling through space. To us, it's everything. We could spend a lifetime exploring its hidden valleys and deepest trenches and still only know a fraction of its wonders. Its circumference is 40,000 kilometers, a distance that would take a commercial jetliner nearly 2 full days to circle without stopping. It feels, for all intents and purposes, immense. But let's take our first step outwards. Let's rise above the atmosphere, watching as continents shrink into patterns of green and brown, and oceans merge into a single, seamless blue. From here, we can see the moon, our constant companion. It hangs in the blackness, about 400,000 kilometers away. A beam of light, the fastest thing in the universe, takes a little over 1 second to travel from the Earth to the moon. This is our first new unit of measurement, the light second. It's the yardstick we'll need for the journey ahead. Now, let's pull back further. The Earth shrinks to a marble, then a pebble, then a pinprick of blue light. We're now looking at our solar system. At its center is the Sun, a star of blistering thermonuclear fire, so large that you could fit over 1 million Earths inside it. Around it, the planets dance in their ancient, gravitational ballet. The light that leaves the Sun takes just over 8 minutes to reach Earth. We are 8 light minutes from our star. If we were to travel to Jupiter, that journey for a photon of light would take over 40 minutes. To reach Saturn, well over an hour. The distances are already becoming hard to grasp. But we're still in our own backyard. Let's keep going. We pass Uranus and Neptune, ice giants slumbering in the cold outer dark. We eventually reach Pluto, the demoted dwarf planet, a tiny world of frozen nitrogen and methane mountains. Light from our sun takes over 5 hours to reach this distant outpost. We've now traveled 5 light hours. And we still haven't even left home. For a long time, this was considered the edge of our solar system. We now know that's not true. The true boundary lies much, much further out. Surrounding our entire planetary system is a theoretical, ghostly sphere of icy bodies known as the Oort cloud. It's a vast, diffuse shell of trillions of comets, loosely bound to our sun by the faintest whisper of gravity. We've never seen it directly, but we see its calling cards in the long-period comets that occasionally fall into the inner solar system, blazing to life as they near the sun. How far away is this final frontier of our solar system? The Oort cloud may extend a quarter of the way to the next star. In our new language of light, it could be more than a asterisk light year across. Think about that. An object so vast that it takes light an entire year to cross it is still considered part of our own solar system. This is our true cosmic address, a tiny family of planets, huddled close to a star, wrapped in a vast, invisible sphere of ice, adrift in an even greater sea of black. And now, with this first, dizzying sense of scale in our minds, we're ready to take the next step, to leave our home behind and venture out into the city of stars. The city of stars. Our galaxy. Leaving the outer fringes of the Oort cloud, we float in the interstellar medium. The sun is now just the brightest star in a sea of countless others. The emptiness here is profound, a vacuum more perfect than anything we can create on Earth. The nearest star to our own, Proxima Centauri, is 2 light-years away. To put that in perspective, if the sun were a grapefruit in New York City, Proxima Centauri would be another grapefruit in San Francisco. The space between them is almost entirely empty. This is the nature of the cosmos, immense voids punctuated by tiny islands of matter. Let's travel that 4-year journey of light in an instant and arrive at Proxima Centauri. Looking back, our sun is just another bright, unremarkable star. Now, let's pull back again, faster and faster. The stars, once distinct points of light, begin to blur together. A shape emerges from the darkness, a breathtaking, swirling structure of light, gas, and dust. We're now looking at our home galaxy, the Milky Way. It's a barred spiral galaxy, a colossal Catherine wheel of stars spinning slowly in the void. From here, we can see its structure. At the center is a bright, dense bar of older, yellow stars. At its very heart, hidden from our eyes, lies a supermassive black hole, 4 million times the mass of our sun, its gravity orchestrating the galaxy's majestic rotation. From this central bar, great spiral arms curve outwards. These are the stellar nurseries of the galaxy, ablaze with the light of hot, young, blue stars and threaded with glowing pink nebulae where new stars are being born right now. Our sun, and our entire solar system, resides in one of these arms, a smaller spur known as the Orion Arm. We live in the galactic suburbs, about 2/3 of the way out from the galactic center. The sheer scale of this stellar city is, again, almost beyond comprehension. If our entire solar system, out to the edge of the Oort cloud, were the size of a dinner plate, the Milky Way galaxy would be the size of North America. It's about 100,000 light-years from end to end, 100,000 years for light to cross it. It contains somewhere between 100 and 400 billion stars. For every person who has ever lived, there are dozens of stars in our galaxy alone. And surrounding this disk is a vast, spherical halo of older stars and mysterious dark matter, extending even further into the void. Take a slow breath. Let that sink in. Billions of stars, each a sun. Billions of potential solar systems, all held together by gravity in a single, magnificent structure. This is our galaxy. And yet, for all its grandeur, it's just one of many. Our journey is only just beginning. The neighborhood of galaxies. For a long time, we thought the Milky Way was the entire universe. Those faint, fuzzy patches of light we saw through telescopes were called spiral nebulae and were believed to be gas clouds inside our own galaxy. It was only about a century ago we realized the truth. They were other galaxies, other island universes, just as vast as our own, seen from an incredible distance. Our nearest major galactic neighbor is the Andromeda Galaxy. It takes a photon of light 2.5 million years to travel from there to here. When we look at Andromeda, we are seeing light that began its journey when our earliest human ancestors were first walking the plains of Africa. It's larger than the Milky Way and is moving toward us. In about 4.5 billion years, our two galaxies will collide and merge into a new, even larger galaxy. The Milky Way and Andromeda are the two giants in a small gathering known as the Local Group. This group contains over 50 galaxies, most of them small, dwarf galaxies, faint wisps of stars orbiting the two big ones. The entire Local Group is bound together by gravity, a small family spanning about 10 million light years. This idea of gravitational grouping is key. Just as stars form galaxies, galaxies form clusters. Our Local Group is a pretty small one. To find a true metropolis of galaxies, we need to zoom out again, to the outskirts of a much larger region, the Virgo cluster. The Virgo cluster is the heart of our local cosmic neighborhood. It contains over 1,000 galaxies packed into a region about 15 million light years across. At its center are several giant elliptical galaxies, cosmic behemoths that grew by cannibalizing smaller galaxies over billions of years. All the galaxies in our Local Group, including our own Milky Way, feel the immense gravitational pull of the Virgo cluster. We are, in a very real sense, falling toward it. But even this colossal city of galaxies isn't the final word. In 2014, astronomers redefined our place in the universe once more. They mapped the movements of galaxies and discovered that the Virgo cluster and our own Local Group are all part of an even grander structure, a supercluster. They named it Laniakea, a Hawaiian name meaning immeasurable heaven. Laniakea is a vast network of filaments and clusters, all flowing toward a central point of immense gravity known as the Great Attractor. It contains roughly 100,000 galaxies and stretches over 520 million light years. To cross Laniakea, light would need to travel for 500 million years. This is our home supercluster, a sprawling web of 100,000 galaxies. The sense of scale is now truly staggering. We've gone from a planet, to a solar system, to a star in a galaxy, to a Local Group, to a supercluster. Each step has increased the scale by orders of magnitude. And yet, we're still just getting started. To find the largest structures, we must look beyond superclusters to the very architecture of the cosmos itself. The cosmic web, the true architecture of the universe. As we continue to pull back our perspective, something extraordinary becomes apparent. On the very largest scales, the universe isn't a random scattering of galaxies and clusters. There's a pattern, an underlying structure connecting everything. Astronomers call it the cosmic web. Imagine a three-dimensional spider's web, impossibly vast, filling all of space. The long, glowing threads of this web are called filaments. These are immense, bridge-like structures made of dark matter, gas, and countless galaxies, stretching for hundreds of millions of light years. Galaxies and galaxy clusters are strung along these filaments like pearls on a necklace. Where these filaments intersect, we find the great nodes of the cosmic web, the most densely populated regions, home to massive galaxy clusters like our own Virgo cluster. And between all of these filaments and nodes lie the voids. These are the great, dark, empty spaces of the cosmos, hundreds of millions of light years across, containing very few, if any, galaxies. While the filaments make up the structure of the universe, the voids make up most of its volume. Our universe is like a cosmic foam, with matter existing on the surfaces of the bubbles, and vast emptiness inside. This magnificent structure, this cosmic web, is the skeleton of the universe. It was seeded by tiny quantum fluctuations moments after the Big Bang and has been slowly growing under the relentless pull of gravity ever since. Dark matter forms the invisible scaffolding, and the visible matter, the galaxies we see, traces its beautiful, intricate pattern. It's within this framework that the true giants of the cosmos reside. The great walls of the universe aren't solid objects, but the largest of these cosmic filaments, or collections of filaments, that we've discovered. For many years, the record holder was the Sloan Great Wall. Discovered in 2003, it's a filament of galaxies some 1.37 billion light-years in length. For a long time, this was considered a shock to the system, a structure so large it was difficult to explain with our models of the universe. But the universe has a habit of shattering our expectations. The Sloan Great Wall was merely a hint of something far, far grander. To find the true Titan, we need to peer even deeper into the cosmic dark, to a place so far away that its light has been traveling for nearly the entire age of the universe to reach us. It's there, in the direction of the constellations Hercules and Corona Borealis, that astronomers found something that wouldn't just challenge our models, but threatened to break them. The Titan, the Hercules Corona Borealis Great Wall. How do you see something that's billions of light-years across? You can't take a picture of it. It's not an object in the traditional sense, it's a pattern, a statistical anomaly spread across a vast portion of the sky. Its discovery required a different kind of vision, a way to map the unseen. The key turned out to be the most violent events the universe has to offer: gamma-ray bursts, or GRBs. A GRB is the death scream of a massive star or the collision of two neutron stars. For a few fleeting seconds, a single GRB can outshine all the stars in its host galaxy combined. They are cosmic lighthouses so brilliant they can be seen from clear across the observable universe. Because these events are tied to massive stars, they tend to happen where there's a lot of matter, in other words, where galaxies are. By mapping the locations of GRBs, astronomers can create a rough map of matter distribution, even where the galaxies themselves are too faint to see. In 2013, a team of astronomers led by Istvan Horvath, John Hakala, and Zsolt Bogoli were doing just that. As they plotted hundreds of GRBs from space telescopes like Swift and Fermi, they noticed something that shouldn't have been there. In a particular patch of the northern sky, toward the constellations Hercules and Corona Borealis, there was a strange overdensity of bursts. A concentration of GRBs, all at a similar and very great distance, seemed to be tracing out a pattern, hinting at an underlying structure of unimaginable scale. They had found the first evidence of what would be called the Hercules Corona Borealis Great Wall.
Let's pause and try to wrap our minds around the scale. Initial estimates suggested the structure was an incredible 10 billion light-years across. More recent analyses suggest it could be even larger. Our own Milky Way galaxy is a mere speck in comparison. You could line up nearly 100,000 Milky Way galaxies, end to end, and they still wouldn't span the full length of this potential Great Wall. The entire observable universe is about 93 billion light-years in diameter. This single potential structure might span more than 10% of the entire cosmos we can see. Its light has taken 10 billion years to reach us, meaning we're seeing it as it was when the universe was less than 4 billion years old. This isn't a solid wall, but a proposed vast, interconnected filament, a superfilament, perhaps of the cosmic web. It's a hypothesized concentration of thousands of galaxy clusters and superclusters, gravitationally linked in a pattern of nearly incomprehensible size. If it's real, it is by a staggering margin the largest structure ever identified by humanity. And that, if presents a profound and unsettling problem. The rule-breaker, controversy and cosmology. The discovery of the Hercules Corona Borealis Great Wall was more than a new cosmic record. It was a direct challenge to one of the most fundamental ideas in cosmology, the cosmological principle. This principle is an assumption, but a deeply important one. It states that, on the very largest scales, the universe is homogeneous, roughly the same everywhere, and isotropic, looks roughly the same in every direction. If you zoom out far enough, the universe should appear smooth, with no significant lumps or bumps. Based on this principle, physicists calculated a theoretical size limit for any gravitationally bound structure. Since nothing can travel faster than light, there simply hasn't been enough time since the Big Bang for gravity to pull together an object larger than about 1.2 billion light-years. Structures like the Sloan Great Wall, at 1.37 billion light-years, were already pushing this boundary. But the Hercules Corona Borealis Great Wall doesn't just push the boundary, it shatters it. At 10 billion light-years or more, it's nearly 10 times larger than the theoretical maximum. It's a cosmic mountain in a landscape that's supposed to be a flat plane. This presents cosmologists with an uncomfortable choice. The first possibility is that the structure isn't real. Some scientists argue the clustering of GRBs is a statistical fluke, a random alignment that just looks like a structure. And this is a valid concern. If you search a large enough dataset, you're bound to find patterns just by chance. However, as more data is collected, the statistical significance of the Great Wall seems to grow, making a random chance explanation less likely. The second possibility is that the structure is real, and our understanding of the universe is fundamentally incomplete. If a structure this large can exist, it means the universe is not as homogeneous as we believed. It could mean the conditions after the Big Bang were lumpier than our theories predict, or that some unknown force has been at work. The jury is still out. The Hercules Corona Borealis Great Wall sits at the frontier of our knowledge, a beautiful and confounding mystery. It is a reminder that the universe is under no obligation to conform to our expectations, and that we are still capable of being completely and utterly surprised. A new contender, the Quipu. While the Great Wall remains debated, the hunt for cosmic giants is always on. And in 2025, astronomers announced the discovery of another magnificent superstructure, this one named Quipu. The name comes from the ancient Inca method of recording information using a complex system of knotted cords, which the structure resembles. Discovered using X-ray surveys that map hot gas in galaxy clusters, Quipu is an immense object in its own right. It stretches for an astounding 1.4 billion light-years and contains the mass of 200 quadrillion suns. What makes Quipu fascinating is that, unlike the Great Wall, its existence is not a matter of statistical debate. It's a prominent feature that is readily noticeable in sky maps of our nearby cosmic neighborhood. At roughly 1.4 billion light-years, Quipu is enormous, slightly longer than the old record holder, the Sloan Great Wall. It stands as quite possibly the largest reliably characterized superstructure found so far. Its existence reinforces that the cosmic web is the fundamental architecture of the universe, but it also highlights just how extreme the Hercules Corona Borealis Great Wall truly is. Quipu is a confirmed mountain range that already pushes the limits of our theories. The Great Wall is a hypothetical mountain range that covers an entire continent. The human connection. Why we stare into the void. We've traveled an impossible distance tonight. From the feel of the Earth beneath us, we've journeyed across light years and galactic expanses to a potential structure that spans 1/10 of our known universe. We've wrestled with numbers that defy intuition and concepts that challenge physics. And through it all, a simple question remains: why? Why do we do this? Why are we so captivated by the largest, the oldest, the most distant? Perhaps the answer lies in our own scale. We exist in a strange middle ground, giants compared to the atoms that make us up, but rendered infinitesimally small by the light years and eons of the cosmos. This fascination with extremes might be our way of trying to find our own measure, to stake out the boundaries of existence and find our place within them. There's a deep, psychological pull to these cosmic scales. It's a form of perspective that can be both humbling and exhilarating. To comprehend, even for a moment, a structure like the Hercules Corona Borealis Great Wall, is to see our own world, our lives, and our concerns in a new light. The daily struggles that feel so all-encompassing can seem, from that great distance, beautifully, reassuringly small. But it's not just about feeling small. It's also about feeling connected. The iron in your blood, the calcium in your bones, the oxygen you are breathing, every atom of it heavier than hydrogen and helium, was forged in the heart of a dying star billions of years ago. Those stars were part of galaxies. And those galaxies, we now know, are threaded together into the magnificent tapestry of the cosmic web. We aren't separate from this. We aren't just observers looking at the universe from the outside. We are the universe. We are a part of this cosmic structure that has, after 13.8 billion years, become self-aware. We are the universe's way of thinking about itself. When we feel that sense of awe looking at the night sky, it is the cosmos experiencing a moment of wonder at its own vast and silent beauty. We are the nerve endings of the universe, and our curiosity is the impulse that travels along the great cosmic filaments, seeking to understand the whole. If this slow journey to the edge of understanding has brought you a measure of peace or a sense of wonder, consider following along for more explorations of science, explained slowly. There is always a deeper layer to uncover, another scale to explore. By subscribing, you join a community of curious minds, all seeking to understand our place in this grand and mysterious cosmos. Our journey is now complete. Let's slowly descend the cosmic ladder, falling back through the scales we've climbed. We drift past the titanic, debated form of the Great Wall, back through the voids and filaments of the cosmic web. We fly past the 100,000 galaxies of our Laniakea supercluster and watch as the Virgo cluster recedes into the distance. We find our own small local group and see the familiar spiral of the Milky Way grow to fill our vision. We plunge into its outer arms, past billions of stars, seeking out that one, unremarkable yellow sun in the Orion Arm. We cross the ghostly sphere of the Oort cloud, past the distant orbits of Neptune and Saturn, and watch as a small blue marble grows larger and larger. The familiar patterns of continents and clouds welcome us home. You are back where you started, in a quiet room, on a small planet. But perhaps something has shifted. Tonight, when you close your eyes, remember the invisible architecture that holds the universe together. Remember the silent, spinning cities of stars and the vast, dark oceans of the void that separate them. Remember the Great Wall, a structure so immense it challenges our knowledge, a quiet testament to the boundless mysteries that still await us in the dark. The universe is not just vast. It is structured, it is interconnected, and we are a part of it. Part 2. What counts as a structure in the universe? When we ask what the largest structure in the universe is, it sounds like a simple question, almost childlike, in a good way. Like asking what the tallest mountain is, or the deepest ocean trench. It feels as if the universe should offer a straightforward answer. Somewhere out there, there must be one thing larger than all the others, one final giant sitting quietly at the top of the cosmic ladder. But the deeper you go, the stranger the question becomes. Because before we can ask what the largest structure is, we have to ask something even more basic. What do we even mean by a structure? That word sounds ordinary, familiar. A structure is something built, something shaped, something that holds together. A bridge is a structure. A city is a structure. A skeleton is a structure. But the universe is not a city planned by an architect. It is not a machine assembled by hand. It is a place where gravity pulls, light travels, matter gathers, and time quietly rearranges everything. So when astronomers use the word structure, they do not just mean something large. They mean something organized, something connected, something that exists not as a random scatter of pieces, but as a real pattern in the dark. And that is where the mystery begins. Because in the universe, size alone is not enough. A cloud can be huge without really being a structure in the deepest sense. A random line of stars can look meaningful from Earth and still be nothing more than a coincidence of perspective. Even some of the most famous shapes in the sky, the constellations we grow up learning, are not true structures at all. Orion looks like a figure because our eyes connect the dots, but those stars are not neighbors in any human sense. They are scattered through space at different distances, only appearing close together from where we happen to be. So the universe teaches a quiet lesson very early. Looking connected is not the same as being connected. To count as a structure, something usually needs more than shape. It needs relationship. It needs some kind of shared reality. The pieces have to belong together in more than just appearance. They have to be linked by gravity, by origin, by motion, or by some deeper pattern written into spacetime itself. And once you begin to see it that way, the cosmos starts to change. A planet, for example, is a structure. That may sound obvious, but it is worth lingering there for a moment. A planet is not just a pile of rock. It is matter gathered so completely under its own gravity that it pulls itself into a rounded form. Its mountains, oceans, crust, atmosphere, magnetic field, even its weather, all become part of one connected physical system. Earth is not just a collection of separate things. It is one world, a coherent whole. A star is also a structure, though of a very different kind. Inside a star, gravity presses inward while heat and radiation push outward. The entire object exists as a kind of long negotiation between collapse and resistance. It glows because its core is dense and hot enough for fusion to begin. It lives because balance, for a while, is maintained. A star is not just matter sitting in space. It is matter organized into a temporary identity. Already, at this level, the universe seems to favor wholeness. Gravity gathers. Matter responds. Shape emerges. Order appears. But then we step outward. Planets belong to solar systems. A solar system is also a structure, though it is looser, more spacious, less intimate. The planets do not touch each other. They are not fused into one body. And yet they are unmistakably related. They orbit the same star. They formed from the same ancient disk of gas and dust. Their histories are entangled. Their futures are shaped by the same center of gravity. Even the empty-looking space between them is not truly empty. It is part of the shared architecture of the system. This is one of the most beautiful features of cosmic structure. It does not always need physical contact. Sometimes relationship is enough. The planets do not need to touch the sun in order to belong to it. The bond is invisible, but no less real. And that idea keeps scaling upward. Stars gather into galaxies. This is where structure becomes more dreamlike, and more difficult for the human mind to hold. A galaxy is not simply a crowd of stars. It is a vast gravitational society. Hundreds of billions of stars can move through one another's influence, orbiting a common center, surrounded by dark matter, threaded with gas, dust, star clusters, black holes, and stellar nurseries. Over immense spans of time, galaxies rotate, collide, merge, stretch, and evolve, but they remain meaningful wholes. They are not accidents of perspective. They are real structures, held together by gravity and history. If you were to drift far enough from the Milky Way and look back, you would not see a random spray of suns. You would see one great island of light, one immense system with a shape, a mass, a center, and a story. That matters. Because the question of the largest structure in the universe only becomes possible once you realize the universe is not random static. It has layers. Worlds inside systems, systems inside galaxies, galaxies inside even larger arrangements. The cosmos is nested, almost like Russian dolls, or perhaps like thoughts inside larger thoughts. And the farther out we go, the more careful we have to be. Because beyond galaxies, the word structure starts to become more slippery. Take galaxy groups. Our own Milky Way belongs to a small gathering called the local group. It includes Andromeda, the Triangulum galaxy, and dozens of smaller dwarf galaxies. This is a structure because the members are gravitationally related. They are not just in the same region by coincidence. They are interacting. Their motions reveal a shared system. Beyond groups, there are galaxy clusters. These are denser, richer gatherings, containing hundreds or even thousands of galaxies. In a cluster, the gravity is stronger, the relationships more intense. Galaxies move through hot gas that fills the space between them. Collisions and mergers are more common. Giant elliptical galaxies often dominate the center. The whole thing behaves like a larger organism made of smaller ones. And then we reach superclusters. This is where the language itself begins to feel slightly overwhelmed. Galaxy, cluster, supercluster. We keep adding bigger words because the old ones stop being enough. A supercluster is not one object in the neat, simple sense. It is a sprawling region containing multiple groups and clusters, linked across enormous distances. For a long time, superclusters seemed like the natural top of the hierarchy, the great continental masses of the cosmos. But even here, astronomers had to ask a difficult question. Are all superclusters truly bound structures in the strictest sense? Or are some of them temporary patterns in a universe that is still expanding, regions that look connected now but will not remain unified forever? This is where cosmic structure stops being a simple list and becomes an argument. Because some things in the universe are tightly bound. A planet is. A star is. A galaxy usually is. But on the largest scales, the expansion of the universe begins to matter. Space itself stretches. Distances grow. Gravity fights to hold patterns together, while cosmic expansion quietly pulls them apart. So not every large arrangement is equally real in the same way. Some are deeply bound systems. Others are looser patterns. Some may remain connected for billions of years. Others may simply be temporary features in the great web of matter. And that brings us to one of the most important ideas in this entire journey. The largest structures in the universe are not solid things. They are not giant walls in the way a human mind first imagines a wall. They are not cosmic skyscrapers or colossal monoliths floating in blackness. They are patterns of matter spread across unimaginable distances. Filaments, webs, chains, regions of overdensity. Long braided strands where galaxies and clusters gather along the invisible scaffolding of dark matter. If that sounds less dramatic than a giant object, it is only because the human imagination still prefers simple shapes. But the truth is stranger, and in its own way, more beautiful. The universe seems to build like frost on glass, like veins in a leaf, like roots moving through soil. It does not merely pile matter into lumps. It stretches matter into networks. This is the cosmic web. And once you understand that phrase, everything changes. The cosmic web is the large-scale pattern of the universe. Matter is not evenly spread in all directions like a mist. Instead, it gathers along filaments, with galaxy clusters forming at the intersections, and immense voids opening between them. The result is not chaos, but texture. Not emptiness, but architecture. When astronomers talk about the largest known structures, they are usually talking about pieces of this web. That is why the question is harder than it first appears. We are not asking for the largest single object in the simple everyday sense. We are asking how large a coherent pattern in the cosmic web can be before it stops being one thing and starts being many. We are asking where relationship becomes too loose to count. We are asking where structure fades into background, and that boundary is not always clean. Imagine standing on a hill at night, looking down at a city. You see bright roads, neighborhoods, bridges, clusters of buildings, patches of darkness. You could call the whole city one structure. You could also call each district its own structure. You could focus on the road network, or the power grid, or the skyline. None of those views would be wrong. They would simply describe the same reality at different levels. The universe is like that, but on scales so large they soften the mind. A galaxy cluster is a structure. A supercluster may be a larger one. A filament connecting many clusters is another. A wall-like arrangement of galaxies across billions of light-years might be a still larger pattern. But where exactly the boundaries lie, and whether the entire thing is truly one coherent structure, can depend on how we define connection. Is shared location enough? Is shared motion enough? Does it need to be gravitationally bound? Does it need a common origin? Does it need to stand out statistically from randomness? These are not trivial questions. They are the questions hidden beneath the famous headline. Before anyone can announce the largest structure in the universe, they first have to decide what counts as a structure at all. And astronomers, being careful people when they are at their best, do not always agree. This is partly why some names in cosmology sound so confident, and yet remain quietly controversial. A Great Wall sounds definite, final, as if someone found the cosmic equivalent of a mountain range and simply measured it. But in reality, these discoveries often begin as patterns in data. An overdensity of galaxies here, a filament there, a clustering of gamma-ray bursts in one distant direction. A structure emerges not because someone sees a neat shape directly, but because multiple lines of evidence suggest that matter is not distributed randomly. In other words, the largest structures are often discovered first as whispers. A slight excess. A map that looks uneven. A pattern that should not be there if the universe were smoother than it is. And then begins the slow work of deciding whether that whisper is real. This is especially important because the universe is very good at fooling us. Human beings are pattern-seeking creatures. We find faces in clouds. We find shapes in stars. We find stories in noise. That instinct helped our ancestors survive, but in astronomy, it can also mislead us. If you look at a large enough dataset, some patterns will appear by chance. The deeper and wider the sky survey becomes, the more careful we have to be about what is truly there and what is simply a statistical mirage. So when astronomers say something is a real large-scale structure, they are not just saying it looks big. They are saying it survives doubt. It remains visible after the maps are corrected. It appears in multiple kinds of observations. It stands out beyond what chance alone would likely produce. It fits, at least partly, into our broader understanding of how matter forms patterns under gravity. And yet, even then, the mystery remains. Because the universe may be more textured than our theories once hoped. This is one of the quiet tensions running through modern cosmology. On the largest scales, the universe is expected to be roughly smooth. Not perfectly smooth, of course, but smooth enough that no single region should dominate too strongly. And yet we keep finding enormous features. Vast filaments. Great walls. Immense superstructures. Some are well established. Some are still debated. But together they suggest that the cosmic web can produce patterns of astonishing scale. This does not necessarily break cosmology. But it does remind us that the universe is under no obligation to be emotionally convenient. We like clean categories. We like final answers. We like a neat list with one clear winner at the top. The cosmos, very gently, refuses. Sometimes the largest thing is not a thing in the ordinary sense. Sometimes it is a pattern. Sometimes it is a network. Sometimes it is a region of enhanced connection, visible only when you step so far back that galaxies become grains and clusters become knots in an invisible lace. And maybe that is fitting. Because the deeper lesson here is that the universe does not build upward like a tower. It builds outward like a web. That is why the word structure becomes so rich on cosmic scales. It no longer means merely an object. It means an arrangement with meaning, a real relationship among separated parts, a persistence that survives perspective, a pattern written into matter itself. By now, the question we began with has changed shape. We started by asking, almost innocently, what the largest structure in the universe is. But now we can ask it more honestly. Are we looking for the largest bound object? The largest galaxy concentration? The largest known filament? The largest reliably characterized pattern in the cosmic web? Or the most extreme candidate ever proposed, even if its full nature remains debated? Each version of the question leads to a slightly different answer. And that is not a weakness. It is part of what makes this topic so quietly captivating. The universe is not confused. It is layered. A child asking what the biggest thing in space is deserves a simple answer. But a deeper answer, the one that keeps astronomers awake and dreamers calm beneath the stars, is this. The biggest structures in the universe are not simple giants standing alone. They are relationships on the grandest scale. They are matter learning to gather. They are gravity writing slow calligraphy across billions of light years. They are the places where the universe reveals that it is not just full of objects, but full of connection. And this is why the story becomes so interesting from here. Because now that we know what counts, or at least what might count, we can move beyond the question itself and into the architecture behind it. We can begin tracing how the universe built these colossal patterns in the first place. How a young cosmos, once almost smooth, became webbed with filaments, clusters, and voids. How darkness gave structure to light. How gravity turned simplicity into complexity. That is where the real grandeur begins. And if you enjoy drifting through these questions slowly, in a way that lets the mind settle rather than race, you can always leave a like, subscribe for more of these quiet cosmic journeys, and tell me in the comments what scale of the universe unsettles you the most. A planet, a galaxy, a supercluster, or the web itself. For now, just hold onto the image. Not of one giant object, but of a universe that builds in layers. A world inside a system, inside a galaxy, inside a cluster, inside a filament, inside a web. And somewhere, tucked inside all of that, a small blue planet turning in silence, while creatures made of stardust ask what the biggest thing is, and slowly realize that the answer may not be a thing at all, but a pattern so vast that only patience can see it. Part 3. How the universe built a cosmic web. If you could step far enough away from everything you know, past the planets, past the stars, past the soft spiral glow of the Milky Way, and keep drifting outward until whole galaxies looked like dust, you might expect the universe to become simpler. Just emptier, perhaps. More random. More still. But that is not what happens. The farther astronomers looked, the more they found that the universe is not a smooth fog of matter scattered evenly through the dark. It has shape. It has texture. It has long strands and crowded knots and vast empty regions between them. On the greatest scales we can map, the universe looks less like a cloud and more like a web. A cosmic web. That phrase sounds poetic, almost too elegant to be scientific, and yet it is one of the most useful ways to describe the architecture of the universe. Not a universe built as a uniform field. Not a universe filled with isolated islands alone. But a universe where matter gathered into filaments, where galaxy clusters formed at intersections, and where unimaginable voids opened between them like silent cosmic oceans. And if that image feels strange, it should. Because it tells us that the largest patterns in existence were not built as solid blocks. They were woven. Tonight, that is the journey. Not simply to admire the web from afar, but to understand how it came to be. How a young universe that began in extraordinary simplicity slowly developed this immense structure. How gravity, time, darkness, and tiny imperfections worked together to turn the cosmos into something layered, connected, and beautifully uneven. And by the time we reach the end of this quiet climb, the largest structures in the universe will begin to feel a little less impossible, because we will see that they were not sudden accidents. They were the natural result of a universe that has been building patiently for almost 14 billion years. To begin, we have to go back to a time before galaxies existed, a time before stars, a time before there was any familiar light at all. The early universe was, in one important sense, astonishingly simple. After the Big Bang, matter and energy filled space in a hot, dense state. As the universe expanded, it cooled. The first atoms eventually formed, light was finally able to travel freely, and the young cosmos entered a long, dark age before the first stars ignited. But even before those stars appeared, something vital was already present. Tiny differences. Not huge differences. Not dramatic ones. Not giant clumps standing out against empty space. Just slight unevenness. Faint variations in density so small that, to the human mind, they might seem trivial. In some regions, matter was a little denser than average. In others, a little less dense. And that was enough. This is one of the deepest habits of the universe. Give gravity even the smallest advantage, and time will turn that advantage into structure. A slightly denser region has slightly more gravity. That extra gravity pulls in a little more matter. As more matter falls in, gravity grows stronger still, which pulls in even more. It is a slow and patient feedback loop, not explosive, not rushed, more like a whisper repeated for billions of years until it becomes a landscape. This is how the web began. At first, there was no need for anything complicated, no need for planets, stars, biology, or thought. All the universe needed was time, gravity, and the tiniest departure from perfect smoothness. If the early universe had been absolutely uniform, if matter had been spread with perfect equality everywhere, then gravity would have had no preferred place to begin its work. The cosmos might have remained far simpler than it is. No galaxies, no clusters, no long filaments crossing the dark. But perfection, it turns out, is not fertile. Imperfection is. Those tiny ancient ripples became the seeds of everything. There is something almost comforting in that. The idea that all this grandeur began not from giant walls or monstrous structures, but from little imbalances. Barely noticeable irregularities in the newborn universe. The great web we see now is, in some sense, the grown-up form of those first faint ripples. Astronomers can still see evidence of this early unevenness in the cosmic microwave background, the oldest light we can observe directly. It is a kind of afterglow from the early universe, spread across the sky. At first glance, it looks nearly uniform, and that near uniformity is itself extraordinary. But when measured carefully, it contains tiny temperature differences. Minute fluctuations. These are not random decorations. They are traces of the young cosmos before galaxies existed, a map of where matter was ever so slightly denser or thinner than average. In a way, the cosmic microwave background is like an ancient blueprint, not a finished building, just the earliest sketch. And when scientists compare that ancient sketch with the large-scale universe we see today, something remarkable happens. The relationship makes sense. Those tiny ripples appear to have grown, under gravity, into the enormous network of galaxies and clusters that now fills the observable universe. But gravity alone is not the full story. To understand the web properly, we have to talk about one of the strangest ingredients in the cosmos: dark matter. Dark matter is one of those phrases that sounds almost mythic until you remember how practical it really is. Astronomers did not invent it because they wanted mystery. They were forced toward it because the visible universe was not enough to explain what they were seeing. Galaxies rotate too quickly. Clusters hold together too strongly. Large-scale structure forms too effectively. Again and again, the gravity from ordinary matter alone does not seem to be sufficient. So when cosmologists reconstruct the universe, they find that most of the matter involved in shaping large-scale structure is not the matter of stars, planets, gas clouds, and people. Most of it is dark matter, invisible to light, but still gravitationally powerful. It does not shine, it does not reflect, and it does not form glowing galaxies on its own, but it helps build the framework within which visible matter gathers. This is why some astronomers describe dark matter as the scaffolding of the universe. Not because it is literally made of beams or lines, but because it created the gravitational backbone along which ordinary matter could collect. Imagine, for a moment, a valley slowly forming in an invisible landscape. You cannot see the valley itself, but you can see water beginning to flow into it. That is somewhat like the role dark matter plays. It sets up the gravitational terrain, and ordinary matter responds. Gas falls into the deeper wells. Regions grow denser. Over long ages, stars ignite inside those concentrations, and galaxies begin to appear where the hidden framework was already guiding matter into place. So when we look out into the universe and see galaxies strung along long filaments, gathered into clusters, and separated by vast voids, we are seeing the visible trace of an underlying structure that is only partly visible. The glowing matter is like frost on a window, revealing the shape of forces we cannot see directly. That is what makes the cosmic web feel so haunting. It is not just made of light, it is light draped over darkness. As the universe aged, these patterns became more pronounced. Small overdense regions grew. Gas cooled and condensed. The first stars were born. Those stars lit up the darkness and began forging heavier elements. Galaxies emerged, not in isolation from all else, but inside larger gravitational environments. Over time, galaxies merged with one another, groups formed, clusters thickened, and long filamentary bridges of matter connected the larger nodes. Meanwhile, the underdense regions went the other way. If one area contains slightly less matter than average, gravity there is weaker. Matter tends to drain away toward denser zones. And as it leaves, the emptier region becomes emptier still. These are the voids, enormous stretches of space with far fewer galaxies than expected. They are not perfectly empty, but compared with the crowded filaments and clusters, they feel almost abandoned. So the web develops in two directions at once. Matter piles up into filaments and nodes, and matter evacuates the spaces in between. The result is not a uniform universe decorated with a few structures. The result is a universe whose very large-scale appearance is shaped by contrast. Crowded strands, dense intersections, giant hollow regions, a lacework of matter stretched across blackness. This is why the web analogy is so powerful. Not because the universe literally resembles a spider's web in every detail, but because its matter is distributed in a network. Long connecting strands, concentrated intersections, empty pockets. A pattern built by tension and relation rather than by one monolithic form. And once you know this, you start to understand why the largest known structures are so hard to talk about in ordinary language. Because on these scales, the universe is not full of giant isolated objects. It is full of giant connected patterns. In the middle of all this, galaxies live out their quieter local stories. Stars are born and die. Black holes feed. Spiral arms rotate. Planets cool. Life, perhaps, emerges in rare corners. But those local stories are still embedded in the web. A galaxy may feel self-contained when viewed up close, yet from far enough away it becomes one luminous speck in a filament, one knot in a much greater architecture. Even the Milky Way, magnificent as it is from our perspective, is not outside this pattern. It belongs to a small group of galaxies. That group belongs to a larger surrounding arrangement. We are not floating in random emptiness. We are residents of a structured cosmos. There is a humbling gentleness to that realization. Human beings spent so long imagining the heavens as a dome of lights, then later as a vast space filled with stars and galaxies. But the deeper view is even more intricate. The universe is not merely full of things. It is full of relationships between things. And scientists did not arrive at this picture all at once. At first, they could only guess. The sky offered limited clues. Galaxies were visible as scattered patches, but the full large-scale map was incomplete. It took generations of better telescopes, deeper surveys, more sensitive instruments, and a great deal of statistical patience to see the pattern clearly. As astronomers mapped the three-dimensional positions of more and more galaxies, the web began to emerge, not as a metaphor first, but as a measurable distribution. Galaxies really were clustering into large filaments and walls. The empty regions really were vast. The cosmic landscape was structured in a way earlier astronomers could barely imagine. Computer simulations deepened this picture even more. When scientists modeled a universe filled with matter, especially with dark matter included, and let gravity act over billions of years, the results were astonishing. Out of near-smooth beginnings, the simulations produced filamentary networks strikingly similar to what large sky surveys were revealing. It was one of those rare scientific moments that feels almost eerie in its elegance. Start with tiny early fluctuations, add gravity, let time pass, and a web appears. That does not mean every detail is fully solved. Far from it. The universe still holds many unanswered questions. We do not yet know exactly what dark matter is. We still refine our measurements of how structure grows. We continue debating the status of particular huge formations. But the broad picture has become one of the most compelling in modern cosmology. The large-scale universe is web-like, and that web was built gradually. This gradualness matters, especially for a channel like this, because the imagination often jumps too quickly to finished wonders. We hear about a giant wall of galaxies or a massive superstructure and instinctively picture something abrupt, dramatic, almost artificial. But the truth is far more patient. The universe did not throw these things together in a hurry. It accumulated them, coaxed them into being, pulled them together a little at a time. A filament spanning hundreds of millions of light years is not the result of one event. It is the result of countless motions, countless gravitational influences, countless local histories woven into a larger shape. Every galaxy in such a structure has its own story, yet together they become part of something much bigger than themselves. This, perhaps, is one of the quiet beauties of cosmology. The largest patterns are built from the smallest differences. The grandest structures emerge from slow accumulation. And what looks fixed and majestic from our perspective is, on deep time scales, still in motion. The web is not a frozen ornament. Galaxies move through it. Clusters merge. Matter flows along filaments toward denser nodes. The architecture endures, but it is alive in the only way the universe knows how to be alive, through motion governed by time and gravity. Of course, the story is complicated by the expansion of the universe itself. Space is not static. It stretches. Galaxies on very large scales are carried apart by that expansion. For a long time, gravity could overcome expansion in local and regional environments, helping structure grow. But the universe is also influenced by dark energy, the mysterious phenomenon driving accelerated expansion. That means there are limits to how tightly the grandest scales can remain connected in the future. Some structures are bound. Others are patterns that exist meaningfully now but may not remain part of a single coherent future whole forever. And that brings a strange kind of poignancy to the cosmic web. It is not merely a map of where matter is. It is also a record of a struggle. Gravity gathers. Expansion separates. The web is what formed in the tension between those two tendencies. If gravity had won more completely, perhaps matter would have collapsed into denser and more concentrated forms everywhere. If expansion had dominated too strongly too early, perhaps the universe would never have built such rich large-scale structure at all. But the cosmos we inherited sits in between, rich enough to weave immense filaments, expanding enough to preserve enormous voids and separations, ordered enough to form patterns, wild enough to avoid becoming simple. Sometimes I think that is why the cosmic web feels so deeply calming to imagine. It is vast, yes, almost unbearably vast, but it is not meaningless spread. It is organized without being rigid, structured without being mechanical. It has the quiet look of something that grew, like tree roots through dark soil, like rivers branching across a continent, like frost threading across glass in winter. Only here the scale is measured in millions and billions of light years, and the medium is the whole universe. If you could somehow watch the cosmos evolve in fast motion, the web would not appear instantly. It would emerge slowly from near uniformity, sharpen over eons, thicken in places, empty out in others, light up as stars and galaxies formed along its invisible lanes. The first view would be almost smooth, then faint patterns, then filaments, then nodes bright with galaxies, then the immense contrast between crowded cosmic cities and near-empty cosmic deserts. And somewhere inside one of those quieter corners, on a minor arm of an ordinary spiral galaxy, a species would eventually appear and begin asking questions about the whole. Questions like how the universe built its web. Questions like whether the biggest things in existence are really things at all, or whether they are patterns of relation. Questions like where we fit. And the answer, at least in part, is this. We fit inside the web, not above it, not outside it, not separate from it. Our galaxy is one luminous thread in a larger arrangement. Our local neighborhood is part of a broader cosmic geography. The atoms in our bodies were forged in stars that formed because matter once gathered in one region rather than another. Even our existence, in the longest chain of cause and effect, depends on those tiny early ripples having been there for gravity to build upon. We are latecomers to an ancient pattern, children of structure. And now, once you hold that in your mind, the next step becomes easier. Because when astronomers announce some enormous wall, filament, or newly mapped superstructure, it no longer feels like an impossible oddity. It feels like a natural extension of the web itself, a particularly vast feature in a universe already predisposed toward networks, strands, intersections, and voids. The biggest structures do not come from nowhere. They are the web becoming visible at its most extreme scale. And that is where we are heading next, toward one of those colossal formations that seems almost too large to accept at first glance. But now we are ready for it. We have seen how the universe learned to gather itself. We have seen how darkness laid the scaffolding, how gravity amplified ancient ripples, and how time turned simplicity into architecture. So if you are enjoying this slow climb through the cosmos, you can gently leave a like, subscribe if you want more calm journeys like this, and let me know in the comments what fascinates you more, the crowded filaments or the giant quiet voids between them. For now, just picture it. Not a blank universe. Not a chaotic one, but a woven one. A dark and silent web stretching across unimaginable distances, with galaxies shining along its threads like dew catching the first light of morning. Part 4. Meet Quipu, the largest reliably characterized structure we know. There are moments in astronomy when a discovery does not feel like the finding of a new object, but like the slow lifting of a curtain. For a long time, the universe seemed large in a way that was difficult enough already. Stars were large. Galaxies were large. Clusters of galaxies were larger still. And then, as our maps improved, the cosmos began revealing something even stranger. Not just isolated giants, but patterns so enormous they almost seemed to belong to a different kind of reality altogether. And somewhere inside that deepening map, astronomers found one of the most extraordinary patterns yet. It is called Quipu. And in this part of the journey, we are going to stay with Quipu for a while. Not as a headline, not as a quick fact to be repeated and forgotten, but as a real place in the architecture of the cosmos. We will look at what it is, how it was found, why astronomers take it seriously, and why it has become one of the strongest answers to the question we began with. Not necessarily the most sensational answer, and not the most controversial one, but perhaps the clearest one, the calmest answer, the one that feels solid under your feet. Because while there are other candidates for the largest structure ever proposed, Quipu matters for a different reason. It is not just enormous. It is enormous in a way that astronomers believe they can actually map and characterize with confidence. The name itself is beautiful. A quipu was an ancient Andean system of knotted cords, used by the Inca and other cultures to record information. At first glance, it could look simple, just strands hanging from a larger cord. But the more carefully you looked, the more meaning it carried. Knots, positions, lengths, relationships. It was structure encoded in thread. That name was chosen because the newly identified cosmic superstructure seemed to resemble one. Not a straight line, not a single lump, but a long, branching arrangement, like a main cord with smaller strands descending from it. A giant, knotted record written not in fiber, but in galaxy clusters and dark matter stretched across the nearby universe. And already, before we even get into the numbers, that tells us something important about the nature of the universe. Its greatest structures are rarely simple. They do not rise like towers. They spread like networks. Quipu was identified in 2025 by a team using galaxy clusters detected in X-ray surveys to map the matter distribution in a large shell of the nearby universe, roughly between 130 and 250 megaparsecs away, which is about 425 to 815 million light-years from us. In that mapped region, Quipu stood out as the largest of the major superstructures they found. The researchers described it as stretching for a little over 400 megaparsecs, or around 1.3 to 1.4 billion light-years, with an estimated mass on the order of 200 quadrillion suns. One Max Planck summary of the work describes it as consisting of 68 galaxy clusters and giving the strongest currently characterized claim to being the largest known structure of its kind. Those numbers are so large they almost stop behaving like numbers. 1 billion light-years is already the kind of distance that resists imagination. Light itself, moving at the fastest speed the universe allows, would need 1 billion years to cross it. Human history disappears at that scale. Civilization disappears. Even the age of our species becomes a tiny flicker. And Quipu extends across a distance longer than that, not as a fantasy or a loose metaphor, but as a measured large-scale feature in the cosmic web. But the most important thing to understand is this. Quipu is not a solid wall. It is not a giant glowing bar across the heavens. If you could somehow leave the Milky Way and float impossibly far away, you would not see one tidy object with a clean outline, the way you might see a planet or a moon. What you would see is something looser and stranger. A long, branching region in which galaxy clusters gather along a shared large-scale arrangement. It is a superstructure, a major feature of the cosmic web, not a cosmic brick. And that distinction matters, because it is exactly what makes Quipu feel more believable, not less. The universe, as we have begun to see, builds in filaments and intersections, not in neat human shapes. So Quipu is large in the way the cosmos prefers to be large. Through connection, through pattern, through relationship across distance. To understand how astronomers found it, we have to step into a slightly different kind of seeing. When most people imagine astronomical discovery, they picture a telescope pointed toward a distant object, capturing some faint patch of light. That does happen, of course. But Quipu was not discovered in that simple, direct way. It emerged from mapping, from pattern recognition, From tracing where galaxy clusters are distributed in space and asking whether they are scattered randomly or arranged into something much larger. Galaxy clusters are useful for this because they are among the best tracers of large-scale matter distribution. They are massive, relatively easy to identify across large distances, and they tend to sit in the denser nodes of the cosmic web. In the Quipu study, researchers used X-ray observations, because the hot gas inside galaxy clusters shines strongly in X-rays, allowing those clusters to be detected and mapped across broad regions of the sky. Once you know where many clusters are, and how far away they are, you can begin to see whether they are isolated, loosely grouped, or part of a major superstructure. This is such a lovely detail, I think, because it reminds us that the universe often becomes visible through its hottest and most extreme environments. Galaxy clusters are not quiet little gatherings. They are colossal systems with galaxies moving through them, dark matter binding them, and enormous reservoirs of gas heated to temperatures so high that they radiate in X-rays. That hot gas becomes part of the map, a hidden thread in the way astronomers learn to see the invisible skeleton of the cosmos. And Quipu, in that map, was unmistakable enough to earn its name, not because it was easy to grasp all at once, but because its pattern stood out strongly enough that the researchers could describe it as the largest cosmic structure discovered to date within their all-sky assessment of nearby superstructures. That phrase matters. It is not just that Quipu is dramatic. It is that it emerges from a careful survey-based approach, rather than from a more speculative or statistically fragile signal. And that brings us to the word that quietly gives Quipu its special place in this story: reliably. Astronomy is full of exciting claims, but not all claims stand on the same kind of ground. Some structures are proposed from indirect clues that are harder to interpret. Some may be real, but controversial. Some may survive and become standard knowledge. Others may fade as the data improve. Quipu is compelling because it sits closer to the sturdy end of that spectrum. It is not merely a provocative possibility. It is a mapped superstructure that researchers can point to, describe, measure, and analyze in connection with known galaxy clusters in the nearby universe. That does not mean the story is over. Astronomy never really gives us final endings. But it does mean that when someone asks, in a calm and careful way, what is the largest structure ever found in the universe? Quipu becomes one of the safest serious answers available right now, especially if we add that important phrase, the largest reliably characterized structure. There is something deeply satisfying about that. Because the universe is already strange enough without our having to exaggerate it, Quipu does not need drama added to it. Its real nature is more than enough. Imagine our own galaxy for a moment. The Milky Way is so large that light needs roughly 100,000 years to cross it from one side to the other. That alone is enough to humble the mind. But Quipu stretches across a scale that makes even the Milky Way feel like a small local detail. Our entire galaxy, with all its stars, nebulae, black holes, and uncounted planetary systems, becomes one tiny element in a much larger fabric. And not just our galaxy. Entire groups and clusters of galaxies become the knots in a single larger thread. This is what the cosmic web does to perspective. It does not merely make things larger. It changes what counts as a thing. Once you start thinking at the scale of Quipu, the universe begins to feel less like a room full of objects and more like a landscape of connected patterns. The boundaries blur. A galaxy cluster is still a structure, yes, but it is also part of a larger arrangement. And that arrangement, in turn, may be part of something greater still. The cosmos becomes nested and flowing at once, a set of scales within scales, each real, each incomplete on its own. Quipu is especially fascinating because it sits in the nearby universe by cosmological standards. That phrase can sound almost funny. Nearby, in this case, does not mean close in any ordinary human sense. It still means hundreds of millions of light years away. But in the context of large-scale cosmology, that region is local enough to matter for more than wonder. Structures like Quipu can influence the way we interpret some of our measurements of the universe. The research team explicitly notes that superstructures of this scale may affect the cosmic microwave background through the integrated Sachs-Wolf effect, distort observations through large-scale gravitational lensing, and contribute to large-scale streaming motions that can influence measurements related to cosmic expansion. In more relaxed language, giant nearby structures are not just scenery. They can subtly tug on the story we tell ourselves about the universe. They can bend light a little, shift motions a little, complicate clean measurements a little. That is one of the reasons astronomers care so much about mapping them. Not because they want a bigger record holder for the sake of headlines, but because understanding these enormous formations helps refine our picture of reality itself. And that, for me, is where Quipu becomes even more beautiful. It is not just the largest of something. It is part of the process by which the universe explains itself to us. The discovery also helps reinforce something we touched earlier. The cosmic web is not just a metaphor. Quipu shows, in a very concrete way, that the web can produce superstructures of astonishing size, enough to dominate major regions of the nearby universe. According to the 2025 study, the largest few superstructures together account for a substantial share of galaxy clusters, galaxies, and matter within the surveyed volume, while occupying only a fraction of the space. That is exactly the kind of uneven, web-like universe modern cosmology has been revealing for decades, matter gathered into strong features, with much emptier regions around them. This is one of those quiet scientific moments where the numbers sound abstract, but the meaning is surprisingly emotional. It tells us that the universe is not bland, not on its greatest scales. It has texture. It has major features. It has immense concentrations and long connective forms that shape whole neighborhoods of cosmic geography. And we, somehow, have become a species capable of noticing. That still amazes me. On one small planet, around one ordinary star, in one ordinary spiral galaxy, matter organized itself into living minds. And those minds looked outward long enough, patiently enough, that they learned to detect a branching superstructure more than 1 billion light-years long. If there is any part of science that feels almost tender, it is this contrast between our fragility and our reach. We are small enough to be broken by a lack of air, yet curious enough to map the largest threads of the nearby universe. Quipu also gives us a chance to speak honestly about how science works when it is healthy. Healthy science is not allergic to wonder, but it does try to separate wonder from overstatement. That is why Quipu is such a useful centerpiece for this topic. It lets us stand on firm ground before we step onto stranger ground later. There are proposed structures in cosmology that may be even larger, and some of them have produced a great deal of excitement. We will get to those. But Quipu is the calm anchor in the middle of the storm. It is the giant that does not need to shout. Its existence alone is enough to stretch the mind. Its mapped shape is enough to remind us that the web is real. Its scale is enough to leave most ordinary intuitions far behind. And because it is nearby enough to be studied in detail, it offers something precious, not just awe, but clarity. If you were to shrink the Milky Way down to the size of a grain of dust in your imagination, Quipu would not become a neat object you could comfortably hold in view. It would remain landscape-like, sprawling, more geography than object. That is one of the reasons beginners sometimes struggle with these topics. We are used to scale producing bigger versions of familiar things. Bigger mountain, bigger animal, bigger planet. But beyond a certain point, cosmic size stops feeling like magnification and starts feeling like a change of category. Quipu is not just a bigger galaxy. It is a different level of existence. A higher order feature of the universe. And once you accept that, something subtle begins to happen in the mind. The question, What is the largest structure in the universe? Stops being a search for a final monster and becomes a meditation on cosmic organization. It becomes a way of asking how far pattern can extend before it fades. How large coherence can become before it dissolves into the general fabric. Quipu gives one answer. A very large answer. A measured answer. A branching answer written across a billion light-year canvas. And yet even here, the universe remains humble in its own strange way. Because Quipu, for all its grandeur, is not the universe itself. It is one feature within the observable cosmos. One major thread among many. One revelation in a map that is still incomplete. There are other superstructures. Other filaments. Other knots. Other regions where matter gathers in forms we are still learning to describe. The discovery of Quipu does not end the story of cosmic scale. It simply gives us one of the clearest markers we have reached so far. A mountain peak, yes, but not the whole world. And perhaps that is why it is so soothing to think about. Not because it makes us feel important, not because it gives us control, but because it places us in a universe that is structured without being exhausted, knowable without being finished. There is still room for surprise, still room for debate, still room for maps to become deeper and stranger. Quipu feels like a signpost in that larger mystery. It says, look how far the web can go. Look how quietly the universe can arrange itself into something immense. Look how much can exist without ever becoming visible to the naked eye. And look how much patience it takes to see the shape of reality properly. That last part may be the most fitting of all for a journey like this. Because Quipu is not a discovery you rush. You do not understand it in one glance. You approach it slowly. First the idea of structure. Then the web. Then the clusters. Then the map. Then the name. Then the scale. And finally, after sitting with it long enough, you begin to feel the full weight of what has been found. A branching superstructure of galaxy clusters. A cosmic cord more than 1 billion light-years long. A major concentration of matter in our nearby universe. A giant pattern that helps answer one of the oldest and simplest questions the night sky can provoke. What is the biggest thing out there? For now, one of the best serious answers is Quipu. Not necessarily the most sensational candidate, and not the final word forever, but one of the clearest giants we have yet learned to trace. And from here, the story becomes even more intimate. Because once you know Quipu exists, the next question almost asks itself. How do human beings, with our small lives and short memories, even begin to imagine something like this? What does it mean to compare the scale of a galaxy, a cluster, a superstructure, and the observable universe itself? How does the mind hold the weight of those distances without letting them dissolve into abstraction? That is where we are headed next. Into the quieter art of comparison. Into the attempt to feel scale, rather than simply quote it. And if you're enjoying drifting through this slowly, you can leave a like, subscribe for more calm journeys through science and space, and tell me in the comments which feels more astonishing to you, the size of Quipu itself, or the fact that human beings were able to notice it at all. For now, just keep the image in your mind. Not a wall. Not a block. Not a single glowing object floating alone. But a vast branching cord in the cosmic dark, a knotted thread of galaxies and gravity, stretching across the nearby universe like a message written in a language the cosmos has been speaking all along. Part 5. Trying to imagine its true size. There is a quiet problem that appears whenever we talk about the universe. Not a problem with the universe itself, but with us. We can hear a number like 1 billion light-years, and we can repeat it. We can say it clearly. We can even write it down and place it inside a sentence. But saying a number is not the same as feeling it. The words arrive easily. The meaning does not. And that is especially true with something like Quipu. A branching cosmic superstructure, stretching across more than 1 billion light-years, sounds impressive immediately. Even someone with no background in astronomy can tell that it must be unimaginably large. But there is a difference between knowing something is large and allowing your mind to slowly settle into what that largeness actually means. That is what we are going to do here. Not rush through the scale, not stack numbers until they turn into fog, but move gently, step by step, from what feels familiar to what no longer does. Because the only way to approach a structure like Quipu is to begin where human imagination still has a foothold. So let us begin close to home. Think of the Earth. Not the Earth as a symbol, not the globe in a classroom, but the real planet itself. Mountains, oceans, deserts, cities, storms turning over the sea, quiet forests in the dark, airplanes crossing continents, people sleeping, people waking, people looking up. All of that exists on a world about 12,700 kilometers across. For most of human history, that already felt infinite enough. Entire civilizations rose and fell without seeing more than a small corner of it. Even now, with satellites and maps and global flights, Earth still feels large to us in daily life. A drive across a city takes time. A flight across an ocean is tiring. The world contains enough detail to fill many lives. And yet in cosmic terms, Earth is almost nothing. If the sun were made the size of a standard front door, Earth would be smaller than a coin. If the sun were a large orange sitting on a table, Earth would be something like a grain of sand several meters away. And even that comparison, gentle as it is, already starts to shift the scale under our feet. Because Earth is not the center of our first real cosmic home. The solar system is. The Earth orbits the Sun at about 150 million kilometers away. That distance, one astronomical unit, is the first rung where ordinary human intuition begins to fail. Light from the Sun takes just over 8 minutes to reach us. That means every sunrise is already slightly old by the time it arrives. We live in a universe where even nearby things come to us with delay. If you move farther out to Neptune, the outermost major planet, sunlight takes about 4 hours to get there. And if you include the icy bodies beyond Neptune, the comet reservoirs, the distant shell of the Oort cloud that may surround the solar system in the far dark, then our system becomes vastly larger than the tidy textbook diagrams suggest. The Sun's family is not a neat circle of planets. It fades outward into remoteness, where objects can take thousands, even tens of thousands of years to complete a single orbit. Already, we are in a place where the human mind prefers to simplify. It wants to shrink everything back into one understandable picture. But the universe resists that comfort. Even our local system is spacious beyond habit. And then, beyond the solar system, there is the nearest star, Proxima Centauri. The closest known star beyond the Sun is about 4.24 light-years away. That means even light, which moves faster than anything else in the universe, needs more than 4 years to cross the distance. A spacecraft built with current human technology would take vastly longer. For all our engineering and ambition, the stars are still mostly beyond touch. They remain, in practical terms, astonishingly distant. This is the first great widening of perspective. The planets that felt so spaced out around the Sun are, in a sense, part of one very tiny neighborhood. The real emptiness begins between the stars. And then comes the Milky Way. Our galaxy is so large that it almost demands a different category of thought. It contains hundreds of billions of stars. It stretches across roughly 100,000 light-years. If a beam of light left one side of the galactic disk, it would still be traveling when everything we call recorded human history had not yet even begun. It would cross the entire age of civilizations, agriculture, writing, empires, religions, industry, the modern world, and still keep going, because the Milky Way is that large. Pause there for a moment. 100,000 years is longer than the existence of cities, longer than the memory of nations, longer than almost everything human beings typically mean when we say, the past. That is just one galaxy. Not the universe. Not a supercluster. Not a great wall. Just our galaxy. When astronomers say Quipu is around 1.3 to 1.4 billion light-years long, one of the simplest ways to begin feeling that number is to compare it to the Milky Way. Quipu is not twice as large as our galaxy. Not 10 times. Not 100 times. It is larger by a factor so extreme that the Milky Way, for all its grandeur, begins to feel less like a major structure and more like a cell in a body. You could place the Milky Way end-to-end thousands upon thousands of times across Quipu's length, and still you would only be beginning to fill the span. And the Milky Way itself is not alone. It belongs to the Local Group, a small gathering of galaxies including Andromeda, the Triangulum Galaxy, and many smaller dwarf galaxies. The Local Group stretches across several million light-years. Even this local gathering, which already sounds immense, becomes a small province once we step outward again. Beyond the Local Group lies the Virgo cluster region and the larger flow patterns of the nearby universe. Galaxies gather into groups, groups gather near clusters, clusters lie along filaments, and filaments compose the cosmic web. This is one of the most humbling truths in astronomy. Scale does not end when the objects become large. It keeps nesting. One level slides into the next. There is always another rung upward. And Quipu lives high on that ladder. It is not a galaxy. Not a cluster. Not a single supercluster in the old simple sense. It is a vast branching superstructure made of galaxy clusters arranged into a major feature of the nearby cosmic web. When you try to compare Quipu with familiar objects, you very quickly run out of familiar objects. That is why analogy becomes necessary. So let us try a few. Imagine the Milky Way as the width of a human hair. Not the thickness of a rope, not the size of a road, just the width of a hair. On that scale, Quipu would still extend for a distance so large it would move well beyond the small world around you. The exact household comparison changes depending on how you scale it, but the emotional truth remains the same. Once Quipu enters the picture, galaxies stop feeling like grand isolated realms and begin to look like tiny details inside a much larger geography. Or imagine Earth reduced to a tiny bead, and the solar system shrunk with it. Even then, the distances between stars would become so large that the model would spread far beyond a room, beyond a house, perhaps beyond a city if scaled honestly. And beyond those stars, galaxies would still sit at distances so much greater that the model would no longer feel like a model of one thing, but of disconnected worlds. Then imagine countless such galaxies gathered into clusters, and those clusters linked into a single giant branching structure. This is what cosmic scale does. It keeps breaking every frame we build for it. Perhaps the better way to think of Quipu is not as an object to be measured against one local thing, but as a change in category. The same way a continent is not simply a larger house, or an ocean is not simply a larger pond. At some point, bigness becomes a new kind of reality. Quipu belongs to that kind of bigness. Another way to approach its size is through time rather than distance. Light from one end of Quipu to the other would take around 1.3 to 1.4 billion years to cross. Try to hold that gently in your mind, not as a number first, but as a span of becoming. Around 1.3 billion years ago, Earth itself was a profoundly different world. Complex life existed, but nothing like human life. No cities, no language, no memory, no history, no faces, no names. The continents were different. The skies were different. The living world was strange and ancient. And yet, if a beam of light had begun crossing Quipu then, it might only now be reaching the far side. That is what one structure asks of light. Not days. Not centuries. Not even the whole of our species' existence. A billion years. And still, Quipu is not the whole universe. Not even close. This is one of the most important balancing thoughts in the entire story. When you first hear about Quipu, it can feel as though astronomy must have reached some final edge. Surely anything over 1 billion light-years long must be brushing against the boundaries of what is possible. But the observable universe is around 93 billion light-years across. That does not make Quipu small. It makes the universe even stranger. It means the cosmos contains room for structures of this size and still extends vastly beyond them. If Quipu is a major mountain range in cosmic geography, the observable universe is still the planet that contains it. That comparison is imperfect, of course, because the observable universe is not a solid territory in the ordinary sense. But emotionally, it helps. Quipu is enormous beyond direct intuition, and still it exists inside something larger. This is one of the deepest patterns in astronomy. Every time we think we have reached enough, the universe quietly reveals more room. And yet Quipu matters precisely because it is not merely large in the abstract. It is large enough to change how we think about structure. It shows that the cosmic web can organize matter on scales that brush up against the limits of our comfort. It forces the mind to confront the fact that the universe is not just populated, it is architected. There is also another subtle difficulty in imagining Quipu. We are used to size being obvious. A mountain is large because you can see its mass. A whale is large because it fills the body's comparison. Even a galaxy, in artistic images, is shown as one glowing form. But Quipu is not visually large in that direct way. Its largeness is distributed. It lives across distance. It is spacious, branching, structured, not dense like a planet or compact like a star. This can make it feel less real at first. But really, it should make it feel more cosmic. Because the universe does not always express greatness through solidity. Sometimes it expresses greatness through pattern, through spread, through relation across vast emptiness. Quipu's immensity is not the immensity of a boulder. It is the immensity of a weather system, a coastline, a route network, a continent-spanning chain. Only here, the scale is no longer earthly at all. You could say Quipu is more like a piece of cosmic geography than a giant object. That may be the best way to hold it. If you think of it as a single thing, in the everyday sense, your imagination keeps reaching for the wrong image. Something block-like, something isolated, something easy to outline. But if you think of it as a gigantic region of interconnected structure in the cosmic web, the mind relaxes a little. It stops asking for a neat silhouette and begins to accept a broader kind of coherence. This is, after all, how the universe seems to prefer building at the largest scales. Not with polished edges, but with connected depth. There is also a psychological side to all this. One reason huge cosmic numbers feel empty is that our brains evolved for survival on a small, local planet. We are good at cliffs, storms, faces, movement in the grass. We are not naturally built to feel the difference between 10 million and 1 billion. Beyond a certain point, both simply become very big. That is not a failure of intelligence. It is a limit of embodied life. The fact that we can even partially understand these scales is already extraordinary. So maybe the goal is not to fully picture Quipu in one mental frame. Maybe that is impossible. Maybe the better goal is to let its scale work on you gradually, the way night works on the eyes. First, you see darkness. Then a few lights. Then shape. Then depth. Then, after a while, you realize the darkness itself has structure. That is what Quipu is like. You approach it indirectly. Through comparisons. Through time. Through the humbling of scale. Through the realization that our galaxy is not central. Our cluster is not central, our neighborhood is not central, and even the biggest mapped superstructures are still part of a larger tapestry. This is why astronomy can be both unsettling and calming at once. Unsettling, because it strips away the false comfort of smallness mistaken for centrality. Calming, because it places us inside something ordered enough to be understood, even if only partially. And Quipu, strangely enough, helps with both. It reminds us that the universe is vast enough to dwarf every human concern, and structured enough that patient minds can still make sense of it. Think of what that means. On one world around one star in one ordinary galaxy, creatures evolved who can sit quietly at night and compare their home to a structure more than 1 billion light-years long. We cannot walk there. We cannot photograph it in one frame like a tourist landmark. We cannot touch it. And still we can trace it, measure it, name it, place it in context. There is something very gentle in that achievement. We remain physically small, yes, but mentally, we have learned to reach. And once you begin to feel the size of Quipu, even a little, you start to understand why the question of the largest structure is so compelling. It is not just about records. It is about the outer limit of coherence, about how far pattern can stretch and still count as a meaningful feature of reality. Quipu gives us one answer, and it is an answer so large that ordinary language nearly breaks beneath it. Yet perhaps that breaking is part of the experience. Some truths are not meant to fit easily inside us. They are meant to stretch us. And this one does. It stretches our sense of distance, our sense of time, our sense of scale, even our sense of what kind of thing the universe is. By the end of a comparison like this, the mind often becomes quieter rather than louder. The numbers stop shouting. The need to master them fades. What remains is something softer. A feeling that the cosmos is not a collection of disconnected marvels, but a layered whole in which structures nest inside larger structures, and where even the largest things we can map are still part of a much greater calm. If you are listening to this while the world around you grows dimmer, while the room becomes gentler and the night settles in, that may be the nicest way to leave Quipu for now. Not as a giant fact to memorize, but as a sense of proportion. Earth is your home. The solar system is your local clearing. The Milky Way is your island of stars. The local group is your neighborhood among galaxies. The cosmic web is the greater landscape. And Quipu is one of its most enormous visible threads. That is where we are. Inside something layered beyond instinct. Inside a universe that keeps widening without becoming meaningless. And if you've enjoyed drifting through these scales, you can leave a like, subscribe for more calm journeys through science and space, and share in the comments which comparison made Quipu feel most real to you: the Milky Way, the age of Earth, or the vastness of the observable universe. For now, let the numbers rest. You do not need to hold all of them at once. Just keep the feeling. A structure so large that light needs more than 1 billion years to cross it. A cosmos so spacious that even that is not the end. And somewhere inside it all, one small world turning quietly in the dark, while a human mind tries, gently, to imagine the size of a thread in the universe's great web. Part 6: How astronomers actually found something this large. There is something almost impossible about the idea of discovering a structure like Quipu. Not because it is too far away. Not even because it is too large. But because it is the kind of thing no one can simply look at in a single glance. You can look at the moon in one frame. You can look at Saturn through a telescope. You can even look at a galaxy, if your instruments are strong enough, and see it as one luminous shape suspended in the dark. But Quipu is different. It is not the kind of thing that reveals itself all at once. It is too spread out, too vast, too woven into the larger cosmic landscape. No telescope gives you one perfect postcard of it. No observer stands back far enough to see the whole structure hanging in space like a neat object with a label. So how do human beings find something like that? How do you discover a structure more than 1 billion light-years long when the universe never hands it to you as a single picture? That is the quiet mystery of this part of the journey. Because finding the largest things in the universe does not work the way people often imagine. It is not like spotting a new island from the deck of a ship. It is closer to mapping a continent in the fog, one ridge, one valley, one river at a time, until a pattern begins to emerge that no one could see from the ground. And that is exactly what astronomers do. They map. They compare. They measure. They gather faint clues from many directions, over many years, and slowly build a picture of a structure that no human eye could ever truly hold in one view. That alone is worth pausing over. Because it means discoveries like Quipu are not sudden flashes of vision. They are acts of patience. The first thing to understand is that astronomers do not usually find giant cosmic structures by looking for the structure itself. That would be too difficult. Instead, they look for tracers, markers, things that reveal where matter is gathering. If you cannot see the whole web directly, you look for the brightest knots tied into it. In the case of Quipu, those knots were galaxy clusters. A galaxy cluster is one of the heaviest things in the universe. Not one galaxy, but hundreds or even thousands of galaxies bound together by gravity, moving through an environment full of hot gas and dark matter. These clusters are like major cities in the cosmic landscape. If galaxies are like houses, then clusters are entire metropolitan regions. They tell you where matter has piled up in especially powerful ways. And because galaxy clusters sit in the densest parts of the cosmic web, they are incredibly useful for mapping large-scale structure. This is one of the great habits of astronomy. You rarely see the thing you most want to understand directly. Instead, you infer it from something else. You see the leaves move and know there is wind. You see a star wobble and know there is a planet. You see galaxies clustered in certain patterns and know there is a deeper architecture underneath. So astronomers began with clusters. But even clusters, immense as they are not always easy to find. Most of the space inside a cluster is dark. The galaxies themselves are luminous, yes, but another important clue lies in something even more dramatic: the gas between them. Galaxy clusters are filled with enormous reservoirs of gas heated to such extreme temperatures that it shines in X-rays. Not visible light, not the gentle colors of human sight, but X-rays, the kind of high-energy radiation that requires very different instruments to detect. This is beautiful in its own way. The largest structures in the universe begin to reveal themselves through some of the hottest environments we know. Vast regions of gas, heated until they glow in invisible energy, become markers on the map. And because space telescopes can detect those X-rays, astronomers can start locating clusters across great distances. That is part of how Quipu came into view. Not as a wall suddenly seen all at once, but as a pattern emerging from the positions of known galaxy clusters. A cluster here, another there, more beyond. Distances measured, directions compared. Slowly, a branching arrangement began to stand out. This is where astronomy starts to feel less like ordinary looking and more like cartography. Imagine living in an ancient world where no one has seen the shape of an entire continent. You only know where towns are, where rivers run, where mountains interrupt the horizon. So you travel, you record. You place one location in relation to another. At first the map is just points. Then the points begin to suggest routes. Then the routes reveal larger patterns. A coastline emerges. A range of mountains. A chain of connected valleys. Eventually, what once felt like separate places becomes one coherent landform. That is how the universe gives up its largest structures, piece by piece. The researchers who identified Quipu were working with large maps of the nearby universe, especially with catalogs of galaxy clusters detected in X-ray surveys. They were not looking at a single photograph and announcing a giant object. They were asking a harder and much more scientific question. When we map galaxy clusters carefully in 3 dimensions, do some of them form larger connected systems that stand out from the background distribution? That phrase, in 3 dimensions, matters more than it may seem. Because when we look at the sky from Earth, almost everything first appears flattened. Stars that are light years apart can seem next to one another. Galaxies at very different distances can appear close from our line of sight. The sky, to the eye, is a dome. But the universe is not a dome. It has depth, real distance. Great layers extending outward in all directions. So if astronomers want to know whether galaxy clusters are truly part of the same structure, they need more than a sky position. They need distance. That is where redshift enters the story, even if we keep it gentle. As the universe expands, light from distant galaxies stretches along with space itself. This stretching shifts the light toward redder wavelengths. By measuring that redshift, astronomers can estimate how far away a galaxy or cluster is. In other words, redshift helps turn the flat sky into a volume. It allows researchers to place objects not just left and right, not just up and down, but deeper into space. Only then can a real structure begin to emerge. Without that third dimension, Quipu would just be a suspicious-looking pattern on a celestial map. With that depth information, it becomes something much more meaningful. A superstructure. A connected arrangement of clusters occupying the same great region of cosmic space. This is one of those points where the science becomes quietly thrilling. Because the sky is full of illusions. Things only look close together until you measure their distance. Patterns only look real until you ask whether the pieces truly share the same neighborhood. Astronomy is, in part, the art of rescuing reality from appearance. And Quipu survived that test. Its clusters were not merely lined up by chance from our perspective. They formed a real large-scale arrangement in space, a major feature in the nearby cosmic web. Still, even that is not enough on its own. Because if the universe is web-like, then clusters will always have neighbors. The question is not just whether objects are close, but whether they are connected enough to count as one larger structure rather than a random portion of the general web. This is where scientific caution becomes important. Astronomers do not simply see a few nearby clusters and declare a giant discovery. They use methods to test how matter is distributed, how overdense a region is compared with the average, and whether the arrangement stands out strongly enough to justify being described as a major superstructure. They compare maps. They look for concentration. They examine shape. They ask whether the pattern is robust or whether it dissolves when analyzed more carefully. In ordinary life, humans are very quick to see patterns. Too quick, sometimes. We see faces in wood grain, animals in clouds, meaning in coincidence. That instinct is ancient, and it often serves us well. But in science, especially in a field as vast as cosmology, you have to be more disciplined. The bigger the dataset, the easier it is for chance to whisper something that sounds meaningful. So astronomers have to ask, over and over, is this really there? Quipu appears to answer yes. Not because it is visually dramatic in a simple way, but because it emerges through careful mapping as a real major concentration in the large-scale distribution of galaxy clusters. It is, in that sense, a discovery born from restraint, from resisting the temptation to speak too early, and instead letting the structure take shape through evidence. That is one reason Quipu feels so satisfying compared with some other giant cosmic claims. It comes from a cleaner kind of detection. Not a single unusual signal, not one ambiguous statistic, but a mapped pattern in the nearby universe that astronomers can describe in detail. And yet, for all its rigor, there is still something poetic about how it was found. Because the method reflects the nature of the universe itself. The cosmos is not laid out for us like a diagram in a textbook. It is scattered across space and time. Light arrives late. Structures are incomplete from any one vantage point. Invisible matter shapes visible outcomes. So of course the path to understanding must also be indirect. Of course we have to reconstruct the great patterns from fragments. We are small creatures inside the web, trying to trace the web while standing on one thread of it. That image never stops moving me. Think about what had to happen for Quipu to become known. First, the universe had to build galaxy clusters over billions of years. Then those clusters had to contain gas hot enough to emit X-rays. Then human beings had to evolve on one small planet and develop mathematics, detectors, telescopes, orbital observatories, and enough shared knowledge to catalog objects millions of times farther away than anything our ancestors could imagine. Then researchers had to gather those clusters into maps, sort their distances, compare their positions, analyze the patterns, and recognize that a giant branching structure was hiding in plain sight. A discovery like Quipu is not just about what the universe contains. It is also about what human patience can do. There is another subtle thing worth noticing here. Quipu was not discovered by going farther and farther into the most remote edge of the universe. In a cosmological sense, it is part of the nearby universe. That word, nearby, sounds almost absurd in this context, but it matters. The structure lies in a region close enough that astronomers can map it with useful detail. That proximity makes the discovery stronger. It means the pattern is not resting on the faintest and most uncertain data. It can be studied as part of our better-known cosmic neighborhood. That gives Quipu a kind of groundedness. It is still astonishingly large, of course, but it does not hover at the limit of detectability like a rumor from the edge of time. It lives in a part of the universe where our maps are becoming more mature, more textured, more reliable. In that sense, Quipu is not just a surprise. It is a sign that our cartography of the cosmos has reached a new depth. And yet, even with the best methods, no one should imagine that astronomers see Quipu the way a bird sees a river. What they see are the parts, the clusters, the positions, the distances, the distribution, the evidence. Then, from those parts, they reconstruct the whole. There is something philosophically interesting in that. It means the largest realities are sometimes the ones least available to direct intuition. You understand them not by looking once, but by connecting many observations across time. In a strange way, that makes Quipu feel even more real. It is not a spectacle. It is a conclusion patiently earned. And that is often how the deepest scientific truths arrive, not as fireworks, as clarity. The more you sit with this, the more the discovery of Quipu begins to resemble the structure itself. A web of information, a pattern assembled from many nodes, a whole that only becomes visible once enough relationships are understood. The method mirrors the object. To find a web, you have to think like a web. This also explains why giant cosmic discoveries often seem to arrive late in human history. It is not because the structures are newly created. They have been there all along. What changes is our ability to map enough of the universe with enough precision to notice them. For most of human existence, even the Milky Way was mysterious. Then galaxies became known. Then clusters. Then superclusters. Then the cosmic web. And now, more and more, specific named superstructures emerge from the map. It is as though the universe has always been speaking in a scale larger than our tools. Only recently have our instruments learned enough of the language to follow along. And still, there is a kind of humility built into all of this. Because even now, our maps are incomplete. There are regions we know better than others. Methods that reveal some features more clearly than others. Structures that seem obvious in one kind of survey and subtler in another. So Quipu is not the end of cosmic cartography. It is one milestone in an ongoing act of discovery. More maps will come. More structure will be refined. Some candidates will grow stronger. Some will weaken. New names will appear. Old boundaries may be redrawn. That is not a flaw in science. It is science doing its work honestly, letting reality become clearer as the evidence deepens. For now, Quipu stands as one of the strongest examples of what that work can uncover. A giant branching superstructure made visible through X-ray selected galaxy clusters, distance measurements, three-dimensional mapping, and careful analysis of how matter is arranged in our nearby universe. In simpler words, it was found the same way all great landscapes are eventually found. By learning how to read the ground. By realizing that separate landmarks are not separate after all. By looking long enough that hidden continuity begins to show. And once you understand that, another question begins to rise very naturally. If astronomers can map a structure this large, and if the universe can build patterns of this scale, then where are the limits? How big can the cosmic web really become before it starts to challenge the picture we thought we had of the universe? At what point does a giant structure stop being merely impressive and start becoming scientifically uncomfortable? That is where the story turns next. Because Quipu, for all its grandeur, is not just a discovery. It is also a warning, a reminder that the universe may be more textured, more extreme, and more willing to stretch our theories than we once expected. And if you've been enjoying this slow journey through the architecture of the cosmos, you can leave a like, subscribe for more gentle science for sleep, and tell me in the comments what fascinates you more, the size of structures like Quipu, or the quiet patience it takes for human beings to find them at all. For now, just keep one image in your mind. Not a giant wall suddenly appearing in the sky, but a map table lit softly in the dark, with clusters placed one by one across it, until at last a hidden pattern reveals itself. A branching thread. A vast cosmic cord. A structure so large no one could ever see it whole, and yet real enough that, piece by piece, the universe allowed us to find it. Part 7. The other giant contender, the Hercules Corona Borealis Great Wall. There is another name that often appears whenever people ask about the largest structure in the universe. And unlike Quipu, this one does not arrive quietly. It arrives with the kind of scale that makes even astronomers pause for a moment. The name is long, a little awkward, and almost easy to overlook at first. The Hercules Corona Borealis Great Wall. Usually shortened to her CRBGW. But once you hear what has been claimed about it, the name becomes much harder to forget. Because if this structure is real in the strongest sense, and if the largest interpretations of it hold up, then it may be far bigger than Quipu, and far bigger than almost any structure people once thought the universe should be able to produce. Early estimates often placed it at around 10 billion light-years across, and more recent work has argued it may extend even farther than that. And yet, for all that grandeur, it comes with an important shadow. It is debated, not dismissed, exactly. Not simply laughed away, but debated in that careful scientific way that matters more than headlines do. Because the Hercules Corona Borealis Great Wall was not identified in the same straightforward survey-based way as Quipu. It emerged through the clustering of gamma-ray bursts, those brief, violent flashes of energy from the distant universe. And that makes the story both more fascinating and more uncertain. So tonight, what I want to do is sit with that uncertainty rather than run from it. Not to flatten the wonder, but to handle it honestly. Because science becomes more beautiful, not less, when it admits where the ground is firm and where it is still shifting. And the Hercules Corona Borealis Great Wall is one of the best examples of that. It may be one of the largest things ever found. It may be a real and astonishing feature of the cosmos. It may also be, at least in part, a pattern made more dramatic by the difficult way we observe the distant universe. The truth is not fully settled, and that unsettledness is part of what makes the story so compelling. To understand why, we have to begin with gamma-ray bursts. Gamma-ray bursts, often called GRBs, are among the most powerful explosions known in the universe. For a brief moment, they can release extraordinary amounts of energy, outshining entire galaxies in gamma rays. Some are thought to come from the collapse of massive stars. Others from the merger of dense stellar remnants like neutron stars. They are sudden, brief, and violent. Little cosmic alarms going off in the dark, visible across enormous distances. That last part is the reason they matter here. Because gamma-ray bursts can be seen from incredibly far away, they give astronomers a way to probe the universe at distances where ordinary mapping becomes more difficult. They are not galaxies in the usual sense, and they are not steady beacons. But they do tell us where extraordinary events happened, and when enough of them are collected with known distances, they can act as rough tracers of large-scale structure. That is where the Hercules Corona Borealis Great Wall first emerged. Back in 2014, a clustering of gamma-ray bursts was reported in a particular region of the sky, mostly in the northern galactic hemisphere, at redshifts around 1.6 to 2.1. In simpler language, astronomers noticed that a surprising number of these distant bursts seemed to lie in roughly the same general region and at roughly similar cosmic distances. That raised an extraordinary possibility. Maybe these bursts were not scattered randomly. Maybe they were pointing toward some immense underlying concentration of matter, some giant large-scale structure far away in the universe. Later studies by the same research group revisited the claim with larger GRB samples and argued that the clustering remained unlikely to be just a simple statistical accident. And that, really, is the heart of the Hercules Corona Borealis story. Not a giant wall photographed directly. Not a crisp filament neatly outlined in a galaxy survey. But a distant overdensity inferred from flashes. A structure seen, in a sense, through fireworks. There is something almost haunting about that image. The universe does not show us the whole thing plainly. Instead, it gives us brief bursts of light, scattered across the deep sky, and asks us whether we can hear the larger pattern inside them. That is one reason this structure captured so much attention. It felt enormous, improbable, almost mythic. A kind of cosmic rumor written in explosions. And if the original interpretation is right, the scale is astonishing. The Hercules Corona Borealis Great Wall has often been described as being on the order of 10 billion light-years across, vastly larger than structures like Quipu. Some more recent analysis from 2025 argues that the same general clustering may extend across an even broader redshift range, suggesting the feature could be larger than originally thought. If that interpretation survives scrutiny, then we are dealing not just with a giant structure, but with something so large it immediately begins pressing against our assumptions about how smooth the universe should become on very large scales. Now, when people first hear that, the instinct is usually the same. How can something that large even exist? And that instinct is reasonable. For a long time, cosmologists expected the universe, when averaged over large enough scales, to become roughly homogeneous. Not perfectly uniform in every local detail, of course, but smooth enough that no single structure should dominate on truly enormous scales. There has long been debate about where that effective smoothness sets in, but numbers around a few hundred megaparsecs often appear in those discussions as an approximate scale where the universe should start looking statistically even. The Hercules Corona Borealis Great Wall, if interpreted as a genuine single structure on the most dramatic estimates, is far beyond that kind of comfort zone. And that is why it has become so famous. Not just because it is large, but because it is uncomfortably large. It is the sort of claim that makes people lean closer to the map. The sort of discovery that tempts headlines into certainty. The sort of thing that can be described as the biggest structure in the universe, and still leave scientists quietly arguing in the background about what exactly that sentence should mean. Because here is the crucial difference between her CRBGW and Quipu. Quipu is a large, nearby superstructure mapped through galaxy clusters in a relatively direct and survey-grounded way. Hercules Corona Borealis is more indirect. It is inferred from the sky distribution of gamma-ray bursts, and gamma-ray bursts are tricky things to build giant conclusions on. They are rare. They are transient. Their detection is affected by where instruments are looking, how sensitive they are, how follow-up observations are done, and whether redshifts can be measured successfully afterward. That does not make them useless. Far from it. But it does make them harder to treat as simple, clean tracers of structure. This is where the story becomes less about raw scale and more about scientific maturity. Because sometimes the most honest sentence in science is not yes or no, It is. Maybe, but carefully. A 2020 re-examination of the Hercules corona borealis evidence argued that the earlier statistical tests may have overstated the significance of the clustering. That paper found that Monte Carlo simulations could reproduce similar anisotropies more easily than the original claim suggested, and concluded that the existence of the structure should be treated as doubtful at best. That is strong language, and it matters, because it reminds us that not every impressive-looking pattern in sparse data becomes a settled feature of reality. At the same time, the story did not end there. A 2025 paper using a newer methodology and a larger GRB dataset argued again for the existence of the Hercules corona borealis clustering, and even suggested that it may extend across a wider redshift span than previously thought. In other words, one line of work remains skeptical, while another continues to find reason for confidence. That does not make the answer impossible. It simply means the structure sits in a live zone of scientific debate. And I think that is worth hearing slowly, because uncertainty has a different emotional weight when you let it breathe. In everyday life, uncertainty can feel like weakness. In science, uncertainty is often where the real work lives. It is the place where evidence is being tested instead of merely repeated. The place where researchers ask whether a pattern comes from the universe itself, or from the way we happen to sample the universe. The place where wonder is forced to share a room with discipline. That is exactly the room Hercules corona borealis lives in. There is also another subtle point here. Even if a clustering is real, that does not automatically mean it is one tidy, bound, wall-like object in the everyday sense. Just as with Quipu, language can mislead us. The term, Great Wall, sounds solid. It sounds like a clean edge in space. But the universe rarely builds like that. More likely, if something like the Hercules corona borealis structure is real, it would represent a broad, loose, large-scale overdensity in the cosmic web, perhaps made up of multiple connected or semi-connected regions rather than one clean slab of matter. That distinction matters because words shape imagination, and imagination, left alone, tends to build the wrong picture. It imagines a glowing barrier stretching through space like a cosmic cliff. But what astronomers are really talking about is much stranger and softer than that. A region of the universe where certain tracers appear unusually clustered. A pattern in the large-scale distribution of matter. A possible feature of the web so enormous that the usual language of structure begins to strain. In that sense, Hercules corona borealis is almost the perfect name for this stage of the story. Not because it gives us closure, but because it denies us easy closure. It says the universe may be capable of structures so vast that we are no longer just measuring them. We are negotiating with them conceptually, trying to decide not only how big they are, but what kind of thing they are. That is a very deep scientific moment. It is one thing to measure a mountain. It is another to realize you are not entirely sure whether what you are looking at is one mountain range, several overlapping ranges, or a pattern that only appears as a range from the angle you are using. That is where her CRBGW sits. At the edge between discovery and interpretation. At the place where evidence exists, but meaning is still being shaped. And perhaps that is exactly why it became so memorable. Because it touches one of the quietest anxieties in cosmology. The fear that the universe may be more uneven, more textured, and more defiant of our simplifying expectations than we would like. If the Hercules corona borealis Great Wall is real in the strong sense, then the cosmic web may contain features of staggering extent, features that force us to rethink how smooth the large-scale universe really is. If it is not real in that sense, then it still teaches us something essential about how difficult it is to extract reliable structure from rare cosmic events. Either way, it matters. And there is something strangely calming in that. Because often, when people hear that scientists disagree, they assume the subject has become messy or broken. But astronomy has always lived inside this kind of tension. One study points to order. Another points to caution. A later paper reopens the question. A new dataset changes the weight of the evidence. This is not failure. It is the normal texture of a field trying to be honest about a universe too large to hand itself over easily. If anything, Hercules' corona borealis shows science at one of its most human and most beautiful. Not when it declares certainty too quickly, but when it keeps returning to the dark, again and again, asking whether the pattern is truly there. And while it does that, we are left with two slightly different answers to the original question. If someone wants the most careful, conservative answer, the structure to point to without overpromising, then Quipu is still the better anchor. It is the largest reliably characterized structure now commonly discussed in that way. But if someone asks for the giant contender, the colossal proposed feature that may be larger still and that keeps cosmologists looking back over their assumptions, then the Hercules corona borealis Great Wall is the name that enters the room. That distinction is worth holding onto, because it keeps the story honest. Quipu is the stable giant. Hercules corona borealis is the provocative giant. One is easier to stand on. The other is harder to ignore. And together they reveal something profound about the cosmos. The universe is not just large. It is large in ways that challenge the categories we bring to it. It does not merely offer us bigger and bigger objects. It offers us patterns that become harder to classify as they grow. A filament here. A wall there. A superstructure here. A debated overdensity there. At some point, the map stops feeling like a museum of objects and starts feeling like a weather system of matter across spacetime. Maybe that is why these discoveries, and near discoveries, affect the imagination so deeply. They are not just records. They are reminders that reality itself may be more connected, and less neatly bounded, than our ordinary language suggests. And when you think about the Hercules corona borealis Great Wall that way, the uncertainty becomes part of the wonder rather than an interruption of it. Because maybe the deepest question is not simply, is this the biggest? Maybe the deeper question is, how large can a pattern become before even our best maps begin to hesitate? That is a beautiful question. And it leads us naturally to the next step. Because once structures become this large, whether firmly mapped like Quipu or hotly debated like Hercules corona borealis, they stop being just curiosities. They begin to press on cosmology itself, on the idea that the universe should become smooth on great scales, on the comfort that our models might still be telling a mostly simple story. In other words, they begin to make scientists uncomfortable, not in a dramatic way. In a thoughtful way. The kind of discomfort that leads to better questions. The kind that keeps people awake under a calm sky. And if you've been enjoying this slow walk through the architecture of the cosmos, you can leave a like, subscribe for more quiet journeys like this, and tell me in the comments which fascinates you more, the firm clarity of Quipu, or the huge unresolved mystery of Hercules corona borealis. For now, just let the contrast settle in. One giant we can map with relative confidence. Another giant we may still be arguing into existence. Both of them whispering the same thing. That the universe may be far more textured than it first appears, and that sometimes the biggest structures are not only difficult to imagine, they are difficult to prove. Part 8. Why giant structures make scientists uncomfortable. There is a particular kind of discomfort that only science can produce. Not fear, exactly. Not panic. Something quieter than that. It is the feeling that comes when reality is still making sense, but not as neatly as you hoped it would. That is the kind of discomfort giant cosmic structures create. Because on one hand, astronomers expect the universe to have structure. Galaxies are not scattered at perfect random. They gather into groups, clusters, filaments, and walls. That much is not surprising anymore. It is part of the accepted modern picture. The universe has texture. It has a web-like architecture. It has regions where matter pulls more strongly, and others where it thins into great emptiness. But on the other hand, there has always been an expectation that this texture would fade if you looked across a large enough scale. That the universe, once viewed broadly enough, would become smooth in a statistical sense. Not locally identical everywhere, not stripped of all detail, but averaged out, balanced, even enough that no one structure would dominate the whole story. And that is where the tension begins. Because every time astronomers find something truly enormous, something measured not in millions but in billions of light years, the old question returns. How smooth is the universe really? And tonight, that is what we are going to sit with. Not just the structures themselves, but the reason they make cosmologists uneasy. Why a giant wall, arc, ring, or superstructure does not merely sound impressive, but touches one of the deepest assumptions in modern cosmology. We are going to move slowly through the cosmological principle, the idea of large-scale homogeneity, the difficulty of defining what smooth even means, and the strange fact that some giant structures do not necessarily overthrow our models, yet still make the story less comfortable than we once imagined. At the center of this discomfort is something called the cosmological principle. The phrase sounds grand, almost philosophical, and in a way it is. The cosmological principle is the idea that, on sufficiently large scales, the universe is homogeneous and isotropic. In simpler language, it means that if you zoom out far enough, the universe should look broadly the same in all directions and in all large regions. Not because every local detail is identical, but because the overall statistical picture should settle down into a kind of large-scale fairness. Modern cosmology leans heavily on this assumption. The standard model of cosmology, the one often called lambda CDM, is built on it at a very deep level. Recent work still describes observational verification of this principle on scales above roughly 100 megaparsecs as one of the central tests of the standard picture. That last part is important. The cosmological principle is not just a decorative idea, the way a motto might hang on the wall of a discipline. It is structural. It supports the mathematics we use to describe cosmic expansion, matter distribution, and the growth of structure over time. If the universe were wildly uneven even on the largest scales, then many of our most trusted simplifications would become harder to justify. This does not mean all of cosmology would instantly collapse. Real science is usually more resilient than that, but it would mean the clean story gets messier. And giant structures are, by their nature, messy making discoveries. Now, to be fair, the universe was never expected to be smooth on every scale. If that had been the case, there would be no galaxies, no stars, no planets, no life, no one to ask questions at all. Structure had to form. Tiny ripples in the early universe grew under gravity. Matter pooled. The cosmic web emerged. In other words, roughness is part of the plan. But the old comfort came from the belief that this roughness had a limit. That once you averaged over a large enough volume, the bumps would wash out and the big picture would become statistically even. The trouble is that large enough is harder to define than it sounds. Some studies have suggested that galaxy distributions approach a kind of almost homogeneity around scales of roughly 150 megaparsecs per h, while quasar studies have pushed that kind of estimate closer to around 250 megaparsecs per h. At the same time, other work has warned that survey methods and selection function modeling can bias results toward apparent homogeneity more than the real universe may deserve. In other words, even the measurement of smoothness is not perfectly smooth. That is one of the subtler reasons giant structures make scientists uncomfortable. They are not just big. They arrive in a field where the ruler itself is still being argued over. One paper may say the universe becomes effectively homogeneous at one scale. Another may say the test is too dependent on method. Another may agree in broad outline but disagree in detail. This is not a sign that astronomy is broken. It is a sign that measuring the shape of reality across enormous distances is genuinely hard. Still, it means that every new ultra-large structure enters the conversation with more weight than it might otherwise have, because it asks, gently but persistently, whether we declared victory too soon. Take the emotional logic of it for a moment. If the universe is expected to become statistically smooth beyond, say, around a few hundred megaparsecs, then a structure significantly larger than that begins to feel awkward. Not impossible, necessarily. Not automatically forbidden, but awkward. Like a wave in a pond that seems larger than the disturbance that should have created it. You start asking whether it is a rare but acceptable fluctuation, a measurement issue, a selection effect, or evidence that your picture of the pond was too simple. That is exactly the mood that giant structures create. They are not always direct contradictions. Sometimes they are just persistent awkwardness. And awkwardness, in science, can be very productive. Recent discussions of ultra-large structures like the Giant Arc, the Big Ring, and the Hercules Corona Borealis Great Wall have framed them in exactly this way. These discoveries are often described as difficult to understand within the standard cosmological model, not because structure should not exist, but because their scales press against the often cited scale of homogeneity and because their formation is not yet fully understood. The same concern appears in recent GRB-based work, where such structures are described as challenging the principles of homogeneity and isotropy that underlie the standard cosmological picture. Notice the word challenging there. Not destroying, not disproving, challenging. That is a very scientific word. It leaves room for both caution and seriousness. A challenge can be survived. It can also reveal weakness. It can lead to refinement rather than collapse. But it is still a challenge. It still means you cannot relax fully into the simplest version of the story. And perhaps that is why these discoveries unsettle people so effectively, even outside science. They touch something deeper than scale. They touch expectation. Human beings do not mind largeness as much as we mind largeness in the wrong place. A mountain is fine if we expect a mountain. A mountain in the middle of the sea changes the map. That is what these giant structures are like. They are not just large. They are large where simplicity hoped for less. There is also a second layer to the discomfort, and it has to do with language. When cosmologists say the universe becomes homogeneous on large scales, they do not mean that every large region must look bland and structureless to the eye. They mean something statistical. Averaged over enough volume, the distribution should converge toward a kind of sameness. This leaves room for individual large structures to exist. In fact, some papers point out explicitly that the existence of large individual structures does not automatically contradict number count evidence for homogeneity on other measures. What it does mean is that one has to be very careful in assuming how quickly or cleanly that convergence happens, and whether the methods used to infer it accidentally smooth away some of the very irregularities we are trying to measure. That distinction is easy to lose in public conversations. People hear homogeneous and imagine featureless. Then they hear about a giant wall or ring and assume cosmology must be in ruins. But the real tension is softer than that. It lives in the space between statistical smoothness and visible structure. It lives in questions like these. How rare should a structure of this size be? How often should such anomalies appear in a universe like ours? At what point does rare but allowed become rare enough to be suspicious? How much of what we call homogeneity depends on the assumptions built into our surveys? Those are not simple questions. They are not questions you answer in one night, but they are exactly the sort of questions giant structures force into the room. And then there is the third reason these discoveries make scientists uneasy. They are hard to define cleanly. The word structure sounds stronger than it often is. A galaxy is a structure. A cluster is a structure. A supercluster is a structure. But when you start talking about things that span gigaparsec scales, the meaning becomes less tidy. Are we looking at one coherent feature, or several linked ones? Are we seeing an overdense region in the cosmic web, or a single discrete object in any intuitive sense? Are we mapping matter directly, or inferring it through sparse tracers like gamma-ray bursts or absorption systems? The bigger the claimed structure, the more these questions start to matter. Ultra-large structure reviews explicitly note that what counts as homogeneity is not precisely or universally agreed, and that expectations about plausible scale have drifted over time. That means part of the discomfort is conceptual. Not just, can the universe produce this? But also, what exactly are we saying it produced? This is one reason Quipu feels different from some other giant candidates. Quipu is uncomfortable in scale, yes, but relatively comfortable in method. It is based on a more grounded mapping of nearby superstructures through galaxy clusters. It still stretches the imagination, but it does so in a way that feels cartographic. Hercules' corona borealis, by contrast, is discomfort piled on discomfort, enormous scale, rarer tracers, and an active debate about whether the pattern is as significant as it first seemed. One giant asks the theory to stretch. The other also asks the evidence to stretch. And yet Quipu is not harmless to cosmological comfort either. The 2025 Discovery paper describes it as the largest cosmic structure discovered to date in the nearby universe and notes that the handful of largest nearby superstructures account for a remarkably large share of galaxy clusters and matter while occupying a comparatively modest fraction of the surveyed volume. The authors also discuss how superstructures of this scale can affect observations, including gravitational lensing, the integrated Sachs-Wolf effect, and large-scale streaming motions, which means these structures are not just philosophical curiosities. They can influence the measurements we use to describe the universe itself. That is another form of discomfort. Not just that giant structures exist, but that they may complicate the instruments of interpretation. In other words, these features are not merely sitting out there being impressive. They can bend the very light and motion we use to infer the larger cosmic story. The map is not separate from the terrain. The terrain reaches back. There is something almost poetic about that. The biggest patterns in the universe not only challenge the story, they also whisper into the measurements by which the story is told. And then, perhaps the deepest unease of all comes into view. The cosmological principle began partly as a philosophical extension of the Copernican principle, the broad idea that we do not occupy a special place in the universe. Recent work still describes it that way. On large scales, we expect no privileged center, no preferred direction, no special cosmic neighborhood. But when multiple observations begin hinting at dipole excesses, bulk flows, quadrupole signatures, or ultra-large structures that feel more pronounced than expected, the mind starts to wander toward a dangerous question. What if the universe is less statistically modest than we hoped? That does not mean we are at the center. It does not mean all of cosmology is wrong. But it does mean the cleanest philosophical version of the story can begin to feel less restful than before. Some 2025 work testing the cosmological principle on gigaparsec scales describes such anomalies directly, including dipole excesses in radio sources and quasars, unexpectedly large bulk flows, and other large-scale signatures that keep the question of large-scale isotropy and homogeneity alive. When you put all of this together, the discomfort starts to make sense. Giant structures make scientists uncomfortable because they sit right at the fault line between confidence and uncertainty. We are confident the universe has large-scale structure. We are less confident about exactly how and where statistical smoothness takes over. We are confident the cosmological principle works well enough to support a very successful standard model. We are less confident that every anomaly is trivial. We are confident that some giant structures are real. We are less confident about whether their size, frequency, or interpretation fits as comfortably as we once imagined. That is not a crisis. It is a pressure point. And pressure points are where understanding often deepens. There is a very human temptation to want science to sound calmer than it is. To say, yes, the universe is smooth on large scales, and yes, there are giant structures, and yes, all of this fits together perfectly, and now we can all sleep peacefully. But the truth is a little more textured than that. The broad model works remarkably well. At the same time, the details continue to push against it. Large-scale structure studies, homogeneity studies, selection function critiques, and anomaly searches all remind us that the cosmic story is still being refined. And maybe that should comfort us more, not less. Because it means the universe is still alive as a scientific landscape, still able to resist complete flattening, still capable of giving us answers that are good, but not too easy, still willing to let a billion light-year structure sit quietly in the dark and ask, "Are you sure your averages are telling the whole truth?" I think that is why giant structures stay with people, not simply because of their size, but because they reopen the oldest tension in human thought, the wish for order, and the suspicion that order may be more subtle than our simplest formulas. Quipu, Hercules' Corona Borealis, the giant arc, the Big Ring, and others like them are not just entries in a cosmic record book. They are tests of temperament. They ask whether cosmology can remain calm while reality gets awkward, whether a model can be both successful and unfinished, whether scientists can hold confidence and doubt in the same hand without dropping either. At its best, science can. That is what makes this discomfort so useful. It is disciplined discomfort. A discomfort that leads not to panic, but to better surveys. Not to collapse, but to improved statistical methods. Not to abandoning the standard model at the first sign of strain, but to asking where its assumptions are strongest, where they are weakest, and where the universe may still be trying to surprise us. And perhaps the most calming thought of all is this. Even if giant structures make cosmologists uncomfortable, they do not make the universe chaotic. They make it richer. They remind us that smoothness, if it comes, is something earned through scale and statistics, not a cheap absence of pattern. They remind us that order in the cosmos does not always mean simplicity to the eye. Sometimes it means the persistence of a rule despite local grandeur. Sometimes it means a web whose largest threads are still thick enough to trouble the map. That is a very beautiful kind of order. An order with room for astonishment. And if you are enjoying this slower walk through the edges of cosmic understanding, you can leave a like, subscribe for more quiet science for deep sleep, and tell me in the comments what feels more surprising to you. That the universe may contain structures this large, or that modern cosmology still has to wrestle so carefully with what smooth really means. For now, just let the discomfort settle into something gentler. Not a threat, not a contradiction, just a reminder that the universe is under no obligation to be simple at the exact scale where human beings hoped it would be. Part 9. Does the universe have a limit to how large structures can get? There is a question that arrives very naturally after everything we have explored so far. If the universe can build things like Quipu, and if it may even contain stranger and more controversial giants beyond that, then where does it stop? Is there some final ceiling? Some invisible cosmic rule saying, this far and no farther? Or can structure keep growing without limit, weaving ever larger patterns into the dark until the very idea of scale loses meaning? It is a beautiful question, because it sounds simple, but it opens into some of the deepest ideas in cosmology. It leads us into the early universe, into the growth of matter under gravity, into the quiet interference of dark energy, and into a humbling realization. The universe may not have one single, easy size limit for structure in the way a planet has a diameter or a star has a surface. What it seems to have instead are several different kinds of limits, working together. Some are statistical, some are dynamical, some come from the age of the universe itself. and some come from the fact that the cosmos is expanding faster and faster, making it harder for gravity to keep building ever larger coherent systems. So the calm answer, at least within standard cosmology, is this. There is probably no single magical number beyond which the universe is absolutely forbidden to produce large patterns. But there are strong reasons to expect that truly enormous structures should become rarer, looser, less bound, and harder to grow as scale increases. In other words, the universe does seem to resist unlimited structure, just not with one clean wall. It resists it through probability, through time, and through expansion. To understand that, we have to begin at the beginning again, with the seeds of structure. The universe did not start with galaxies, clusters, or filaments already built. It began astonishingly smooth, though not perfectly smooth. Tiny primordial fluctuations were present in the early cosmos, and those fluctuations later grew into the structure we see today. Modern large-scale structure theory still treats those early density perturbations as the first stage of cosmic web formation. Without them, there would have been nothing for gravity to amplify. But because those early ripples were small, and because their statistical pattern was close to uniform on very large scales, the universe did not begin with giant ready-made walls. It began with faint unevenness that had to be patiently enlarged over billions of years. That matters, because it means structure growth is not arbitrary. You do not get infinitely large features for free. You only get what the initial ripples, gravity, and cosmic time can build together. If the early universe had contained much larger departures from smoothness, then perhaps the largest structures today would be even more extreme. But the universe we actually observe appears to have started from comparatively gentle fluctuations, and that already places a kind of soft boundary on what later growth can achieve. The cosmic web is immense, but it grew out of modest beginnings. Then comes the second limit, and this one is quieter. Even if the early seeds existed, structures still need time to grow. Gravity works patiently. It gathers matter, deepens overdensities, and pulls regions into denser nodes and longer filaments. But the universe is not infinitely old. It has had only a finite amount of time to turn small fluctuations into large arrangements. So when we ask whether there is a maximum size for structure, part of the answer is simply that the cosmos has only had so many billions of years to do its work. The largest patterns we see are what gravity managed to build before other cosmic effects began to interfere more strongly. And that interference has a name: dark energy. This is where the story becomes especially important. For a long stretch of cosmic history, gravity had the upper hand in shaping structure. Matter dominated the dynamics of the universe strongly enough that overdense regions could keep growing. But in the later universe, dark energy became increasingly important, and with it came accelerated expansion. Once that happened, the growth of large-scale structure began to slow. A major review of structure growth explains this very directly. Dark energy suppresses the growth of structure, reducing how efficiently density fluctuations keep building over time. This is one of the most elegant and melancholy facts in cosmology. The universe is still expanding, and not only expanding, but accelerating. That means gravity is no longer working in the same hospitable environment it had earlier on. It is as though structure formation had a long growing season, and then winter began to set in. Not a violent winter, a slow one. A quiet reduction in the universe's willingness to let larger coherent things form. Existing structures can remain. Local mergers can continue. Bound regions can still evolve internally. But the grand growth of structure on the largest scales is being choked off. This already gives us one powerful answer. If you ask whether structures can grow forever larger in the future, standard cosmology says probably not in any strong sense. The accelerated expansion driven by dark energy means that growing perturbations gradually freeze out, and the future universe approaches a state where existing structures become more isolated rather than more connected. Old simulations of cosmic future evolution described this very clearly. As vacuum energy takes over, growth on all scales freezes and bound systems become isolated, island universes. That language may be old, but the physical picture remains deeply influential and conceptually stable. So if we keep the question simple, does the universe have a future limit to structure growth? The answer is yes. Dark energy effectively imposes one, not by forbidding all motion, but by making it increasingly difficult for matter on very large scales to collapse into anything newly coherent. The cosmic web does not keep knitting itself into ever larger and tighter patterns forever. Its major architecture emerges, matures, and then slowly stops growing in the same way. But there is an even more intimate kind of limit, one that applies not just to patterns in general, but to bound structures with a given mass. This is where cosmologists sometimes use the idea of the maximum turnaround radius. The phrase sounds technical, but the idea behind it is beautifully simple. Imagine a large structure, perhaps a cluster or supercluster region, trying to hold itself together. Gravity pulls inward, trying to keep its outer parts bound. Dark energy, through the accelerated expansion of the universe, effectively pushes the large-scale background in the opposite direction. The turnaround radius is the distance where those tendencies balance. Beyond that scale, matter cannot remain bound to the structure in the same way. In this framework, each structure with a given mass has a maximum possible size it can hold against the accelerating universe. This is a remarkably calming concept, because it tells us that the universe does not allow bound structures to grow without end. There is, for any mass, a practical outer limit to coherence. Beyond that distance, gravity loses the tug of war. One review puts it plainly: the maximum size of a cosmic structure is given by the scale where attraction due to its mass is balanced by the repulsion associated with dark energy. Another notes that beyond this radius a test particle cannot stay bound and will instead be carried away by the accelerated expansion. Now, that does not mean every claimed giant structure must fit neatly inside one turnaround sphere. That would be too simple, and the universe is rarely that tidy. Many of the largest known structures are not single-bound objects in the strong classical sense. They are large-scale patterns in the cosmic web, often made of multiple clusters, filaments, or overdense regions. So when we ask whether Quipu or other enormous features violate a maximum size rule, the answer depends on what kind of structure we mean. A bound cluster is one thing. A giant filamentary pattern extending across many regions is another. The largest structures are often less like one giant ball and more like geography, which means some of them may be real without being gravitationally bound as one future stable whole. That distinction is very important, because it may be the key to why the universe can appear to contain structures of astonishing scale without necessarily breaking all its own rules. Very large features may exist statistically and observationally as patterns, while still not being one eternally bound object. In other words, the web can draw very long lines without those lines being the same kind of thing as a galaxy cluster. This softens the paradox. It suggests that the universe's biggest structures may be large in the language of pattern before they are large in the stricter language of binding. There is also a statistical limit, and this one may be the most subtle of all. The cosmological principle does not say giant structures are impossible. It says that on sufficiently large scales, the universe should become statistically homogeneous and isotropic. But as one recent review points out, there is no single universally agreed definition of that principle, and expectations for what counts as a plausible homogeneity scale have drifted over time. Another important point from the same discussion is that the existence of even the largest observed structure does not automatically violate the principle by itself. The question is not only whether one giant pattern exists, but how often comparable patterns should appear, and whether the universe still averages out overall. That means the universe may not have a hard statistical cutoff either. Instead, it may have a curve of plausibility. As structures get larger, they should become rarer. Their existence may become more surprising. Their interpretation may become more delicate. But rarity is not the same as impossibility. A universe that is homogeneous in the large statistical sense may still contain occasional very large features, just as a calm ocean may still contain unusually long waves. The real issue is whether the observed giants are rare but allowed, or common enough to suggest that our expectations are too simple. So when people ask whether the universe has a size limit for structure, the most honest answer is probably this. For bound structures, yes, there is a meaningful practical limit tied to gravity and dark energy. For large-scale patterns, there is no single simple wall, but there are statistical expectations, finite growth time, and accelerating expansion that all work against unlimited size. The bigger the feature, the more carefully astronomers have to ask what kind of thing it is. A bound object? A filament? A loose overdensity? A tracer-defined pattern? A coincidence enhanced by sparse data? The answer changes with the category. And there is one more limit we should mention, because it gives the whole question a strangely tender ending. The observable universe itself is finite in what it can show us. Not necessarily finite in total existence, but finite in the region from which light has had time to reach us. So even if structure beyond our horizon were arranged into even grander patterns, we could never map them as part of one directly observed whole. The horizon is not just a technical boundary. It is also a limit on cosmic cartography. There may be larger connected realities beyond what we can see, but from our point of view, the universe only offers us a finite stage on which to search for the largest structure. That gives the story a quiet shape. The early universe limits the seeds. Finite time limits the growth. Dark energy limits the future. Turnaround limits the size of what can stay bound. The horizon limits what can ever be observed as one map. Put together, those constraints suggest that the universe is not a place where structure can grow forever in any unlimited sense. It is a place where structure blooms, matures, stretches astonishingly far, and then meets resistance from the deeper geometry of cosmic expansion. And maybe the most beautiful part is that none of this makes the universe feel smaller. It makes it feel more carefully balanced. The cosmos is generous enough to build galaxies, clusters, superclusters, filaments, voids, and patterns that can stretch across 1 billion light-years or more. But it is also disciplined enough not to let everything collapse into one endless bound empire of matter. Gravity gathers. Dark energy separates. The web forms in between. That tension is part of why the universe looks the way it does. If one day astronomers confirm even larger structures than the ones we talk about now, that will not automatically mean there is no limit at all. It may simply mean that the statistical tale of the universe is richer than expected, or that our categories need refinement, or that some structures are patterns rather than bound wholes. It may even point toward new physics. But even then, the deep logic would remain. Structure is not growing in a lawless cosmos. It is growing inside a universe with initial conditions, finite time, accelerated expansion, and observational horizons. So, does the universe have a limit to how large structures can get? Yes, but not in the way a ruler has an end. It has limits more like the sea has limits for waves. The water, the wind, the basin, the time, and the weather together determine what can form. In the same way, the early universe, gravity, dark energy, cosmic time, and the horizon together determine how large structure can become. There may not be one final number written across the sky, but there is still a framework that resists endless growth. And perhaps that is the most sleep-friendly truth in all of this. The universe is not heading toward unlimited complexity. It is heading toward isolation. In the far future, the great growth of structure slows, existing bound systems remain, and more distant regions slip away from one another. The largest web we can observe now is, in a sense, being shown to us during a special era, when enough structure has formed to be grand, but not so much time has passed that accelerated expansion has hidden too much of it from view. We live in a rare moment when the map is still visible. That thought always leaves me a little quieter. Not sad, exactly. Just aware. Aware that the universe has given us this window, this era in which minds on one small planet can ask how big structure can get, and can still see enough of the answer to be amazed. And if you're enjoying this slow journey through the deep architecture of the cosmos, you can leave a like, subscribe for more calm explorations like this, and share in the comments what feels more beautiful to you, that the universe can build structures this large at all, or that it also seems to know when to stop. For now, just let the idea settle. Not a universe of endless accumulation, but a universe of grand, temporary coherence. A place where gravity gathered matter into luminous threads, where dark energy slowly began to pull the threads apart, and where the largest structures we can see may be not just records of size, but records of timing. Part 10. What the largest structure says about our place in the universe. There is a quiet moment that often comes after learning something enormous. Not during the first surprise. Not during the numbers. Not even during the comparisons. It comes later, when the facts have already passed through the mind and settled somewhere deeper. A moment when the real question is no longer, how big is it, but what does that size do to us? What does it change inside the way we see ourselves? Because when you hear that the universe contains structures so large that light would need more than 1 billion years to cross them, the discovery does not stay out there among the galaxies. It comes back. It returns to Earth. It returns to the human mind. And sooner or later, it asks something very simple. Where do we belong in all of this? That may be the oldest astronomical question of all. For as long as people have looked up, the sky has never been just scenery. It has always been a mirror of some kind. A place where we project meaning, fear, order, wonder, loneliness, hope. Ancient people saw stories in the stars. Empires built calendars from the heavens. Sailors trusted the night sky to guide them over black water. Children still look up and feel, almost immediately, that strange mix of smallness and curiosity. The cosmos has always had this effect on us. It changes the scale of our inner life. And perhaps nothing does that more strongly than the largest structures. A planet can humble you. A star can humble you more. A galaxy can dissolve your ordinary sense of importance. But a structure like Quipu, or a giant debated feature like the Hercules Corona Borealis Great Wall, does something even stranger. It does not merely tell you that the universe contains large things. It tells you that the universe organizes itself on scales so immense that even galaxies become details. And once that sinks in, the old human instinct to imagine ourselves at the center begins to feel almost impossible to maintain. That is not a bad thing. In fact, it may be one of the gentlest truths science has ever given us. Because learning that we are not central is not the same as learning that we are meaningless. Those two ideas often get confused. But they are not the same at all. For a long time, human beings placed themselves in the middle of things. The earth seemed central because it felt still beneath our feet. The sun seemed to move around us. The stars seemed arranged for our eyes. And in a practical sense, that made emotional sense. We lie from one small viewpoint. We begin with ourselves. Everything important in ordinary life happens locally. Hunger is local. Love is local. Loss is local. Home is local. It is natural that the mind begins there and imagines outward from it. But astronomy has spent centuries gently undoing that instinct. First, Earth stopped being the center of the solar system. Then the sun stopped being the center of the galaxy. Then the Milky Way stopped being the whole universe. Then galaxies themselves became members of larger structures. And now even those larger structures are revealed as threads in a greater web. Each step removes us from the center. And with each step, something interesting happens. Reality becomes less flattering, but more beautiful. That is one of the deepest gifts of science. It does not always preserve our comfort, but it often gives us something better than comfort. It gives us perspective. The largest structures in the universe are perspective made visible. They are reminders that reality is not arranged around human scale. It never was. The universe did not build itself with us in mind as its audience. Gravity did not gather matter in order to produce an inspiring sky for one species on one planet. The cosmic web exists because the laws of nature allowed it to exist. Quipu exists because matter, time, gravity, and dark energy produced a universe where immense patterns could emerge. The structures are not there for us. And somehow that makes the fact that we can understand them feel even more extraordinary. Because if the universe is not centered on us, then our knowledge of it becomes a genuine achievement, not an inheritance, not a privilege built into creation. An achievement that matters. It means that when a human being sits awake at night and wonders how large the universe can become, that question is not small simply because the person asking it is small. In fact, the opposite may be true. The ability of a finite creature to reach mentally toward things so much larger than itself is one of the most astonishing events the universe has produced. I think that is easy to forget. When people first encounter cosmic scale, they often focus only on their own smallness. They say things like, "We are nothing," or "We are insignificant," or "Everything human must be trivial compared with all of this." And it is true that in the language of size, we are very small. There is no need to pretend otherwise. Earth is small compared with the galaxy. The galaxy is small compared with a superstructure. A human life is brief compared with cosmic history. These are not insults. They are simply measurements. But meaning has never belonged only to measurement. A page in a book is small compared with the whole library. That does not make the page meaningless. A heartbeat is brief compared with a lifetime. That does not make it unimportant. And a human mind, though tiny in physical scale, may still be one of the rare places where the universe becomes aware of itself. That thought has always stayed with me. Not because it makes us grand again in some flattering way, but because it gives dignity to curiosity. It says that being small is not the end of the story. To be physically small and mentally expansive is still a remarkable thing. To live on a tiny planet and learn to map billion light-year structures is remarkable. To be born, grow, suffer, love, wonder, and then spend part of one short life asking about the architecture of the cosmos is remarkable. The largest structures do not erase that. They sharpen it. And perhaps they also do something else. They teach proportion. The world of ordinary life has a way of feeling absolute when we are inside it. A stressful day can seem enormous. A conflict can feel total. An ambition can feel like the axis of the universe. We all live this way sometimes, because the mind naturally enlarges what is close. That is part of being human. But cosmic scale offers a strange medicine for that condition. It does not solve daily pain, of course. It does not erase grief or fatigue or worry. But it can place them in a wider frame. It can remind us that our lives unfold inside a universe so ancient and vast that every burden, while still real, stops pretending to be the whole of reality. There is comfort in that, not because the cosmos fixes us, but because it loosens the grip of false centrality. A structure like Quipu does not care about human deadlines. It does not know our names. It does not move for our sake. And that indifference, oddly enough, can be calming. It reminds us that existence is larger than our immediate noise. That the universe has room beyond our private storms. That there are scales at which urgency softens and the mind can breathe again. This is part of why astronomy has always had a spiritual edge, even when it remains fully scientific. Not spiritual in the sense of offering doctrine. Not in the sense of replacing religion or philosophy, but spiritual in the older sense of altering the interior atmosphere of a person, making the mind quieter. more spacious, less trapped inside the small prison of the self. The largest structures in the universe do that especially well. They take the ego by the hand and lead it into a room so large that it stops talking for a while. And silence, sometimes, is exactly what we need. There is another lesson hidden in all this too, and it is about belonging. When we first learn how large the cosmos is, it is easy to feel alienated by it, as if the scale itself pushes us out. As if a billion light-year structure must be evidence that we are accidents in a reality too big to include us. But the deeper truth is gentler. We are not outside the universe looking in. We are not visitors standing apart from the cosmic web. We are made of the same matter, shaped by the same history, governed by the same laws. The atoms in our bodies were forged in stars. Those stars formed in galaxies. Those galaxies belong to larger patterns. And those patterns emerged from the same early universe whose faint ripples became the web itself. So when we ask what the largest structure says about our place in the universe, one answer is beautifully simple. It says we are inside it, not metaphorically, literally. We are local expressions of a cosmic history that stretches back to the beginning of structure itself. We are not separate from the universe studying it from outside. We are one part of the universe studying another part. In that sense, every question we ask is already an act of belonging. That may be the most comforting thought in the whole story. You do not need to be large to belong. You only need to be real. And we are real. Small, yes. Brief, yes. Vulnerable, absolutely. But real. And because we are real, our position inside the universe is not negated by its size. If anything, its size makes our awareness more precious. A mind that can understand only a little still matters, because understanding at all is rare. The web may stretch across unimaginable distances, but somewhere inside it, on one planet among many, reality has produced beings who can ask what the web means. That is not centrality. But it is not nothing. There is also a kind of moral lesson in cosmic scale, though it is a quiet one. The universe does not divide itself by the categories humans cling to so fiercely. Our borders do not appear from deep space. Our arguments do not echo across superclusters. From the scale of the cosmic web, the whole human world is one small shared event. All our nations, languages, rivalries, triumphs, histories, losses, and songs belong to one thin layer of life on one world orbiting one ordinary star. The largest structures do not erase our individuality, but they do place it in a wider and more humbling frame. It becomes harder, after sitting with cosmic scale long enough, to believe fully in the absolute seriousness of many human divisions. Not because they are unreal to those living through them, but because the universe keeps whispering a larger truth. You are one species. You are sharing one world. You are all living inside the same great web. That may sound idealistic, but astronomy makes it very hard to ignore. The farther out you go, the more local all human separation begins to look. The largest structures do not tell us how to behave, but they do reveal how provincial some of our obsessions really are. They remind us that most of what we call the world is actually a very small room. And if that realization is received gently, it can soften a person rather than harden them. It can make life feel less like a competition for central importance and more like a brief chance to witness something extraordinary. Because witness is another form of place. To have a place in the universe does not require being its ruler. Sometimes it is enough to be one of its witnesses, to be present for it, to look, to learn, to feel the scale of it honestly. The largest known structures invite that kind of witnessing. They are too big to own, too old to influence, too far to change. They do not ask for conquest. They ask for contemplation, for patience, for the humility to let the mind expand without needing to dominate what it sees. That is a rare experience in modern life. So much of the world teaches us to react quickly, to judge immediately, to turn everything into use, advantage, status, urgency. But giant cosmic structures refuse that rhythm. You cannot absorb Quipu in a rush. You cannot hold the idea of a billion light-year pattern and stay mentally shallow at the same time. These subjects demand a slower kind of attention, a quieter kind of intelligence. And maybe that is part of their value, too. They train the mind away from noise. That is why a topic like this belongs so naturally in the space before sleep. Not because it is dull, not because it is empty, but because it is spacious. It gives the mind somewhere vast to go that is not stressful, somewhere large enough to dissolve the sharp edges of the day. The largest structures in the universe are, in a way, like landscapes for thought. Places where the mind can wander until its ordinary anxieties become less rigid. Places where a person can feel small without feeling crushed. And perhaps that is the most important distinction of all. Cosmic scale can make you feel small in two very different ways. One way is despairing. It says you are small, therefore nothing matters. The other way is peaceful. It says you are small, therefore you do not have to carry the illusion of being everything. I think the second way is closer to the truth. The universe has never asked us to be large. It has only allowed us, for a little while, to be aware. And awareness, especially awareness touched by wonder, may be enough. When I think about Quipu, or the Great Wall, or the web itself, I do not finally come away feeling erased. I come away feeling located. Not in the sense of knowing my cosmic address with personal significance, but in the sense of knowing that I exist within a hierarchy of scale so beautiful and strange that my life gains texture from seeing it. Earth becomes dearer, not less important, when placed against that backdrop. Human life becomes more fragile and more precious. A night sky becomes more intimate, not less, once you know what hides beyond it. That is another paradox astronomy gives us. The larger the universe becomes, the more tender the local world can feel. A warm room, a quiet breath, a small blue planet, a single human voice in the dark. These things do not become less beautiful because Quipu exists. They become more beautiful because they exist at all. That may be the final answer to our question. What does the largest structure in the universe say about our place in it? It says we are not central, but we are included. It says we are not large, but we are capable of largeness in thought. It says the universe is vast beyond comfort, yet ordered enough that patient minds can trace its patterns. It says our lives are brief, but brief things can still touch truth. It says reality is not built to flatter us, and that is exactly why our understanding of it matters. And maybe, most quietly of all, it says that home is not destroyed by scale. Home survives scale. Earth remains home even inside a universe of giant webs and walls. The human world remains meaningful even beneath superstructures stretching across a billion light years. The night does not become less yours because it belongs to something larger. It becomes more mysterious, more layered, more deserving of reverence. So perhaps the best way to end this journey is not with one final number, or one final claim about which giant wins the record forever. Science may refine that answer in the years ahead. New maps may appear. New structures may be proposed. Debates will continue. The cosmic web will remain larger and stranger than any simple summary can hold. But beneath all of that, one truth stays quietly intact. We are part of this. Not outside it. Not above it. Part of it. One small branch of the story the universe has been telling since its earliest ripples began to grow. And tonight, that may be enough. If this slow journey through the largest structures in the universe has helped you drift a little farther from the noise of the day, you can leave a like, subscribe for more calm explorations of science and space, and share in the comments what feeling stays with you most after all of this: awe, peace, wonder, or that strange comforting sense of becoming smaller in the best possible way. For now, let the question rest. The largest structure may be a giant thread in the cosmic web, a branching arrangement of galaxies and gravity, a pattern so vast that light itself needs ages to cross it. And yet, somewhere within that same universe, on one small turning world, there is still room for a quiet night, a resting mind, and the simple human miracle of looking into the dark and understanding, if only for a moment, that being small is not the opposite of belonging. It may be one of the ways we belong most deeply.